Hi, very good evening, Mr. Marosi. Hope you're doing great. Yeah, okay. So we have done with the earthing system, and today we'll start with lightning protection, capacitor banks, and let's complete this electrical and as well as some ELV works. We'll have a look into it. So the next topic is going to be lightning protection. Like already we have discussed like a few glimpses I have told you like what is this lightning arrestor lightning protection system, right? So after earthing is for the interior of the building and okay, and lightning protection for the exterior protection of the building. Okay, for that purpose, we need this lightning arresters actually, right? We need this lightning arresters. So, what are the components that would be in a lightning arrestor system? So, as you're saying, this building, yes, there's going to be an air rod or a lightning rod, we say, and then this should be connected to a down conductor. Okay, this should be connected to a down conductor, and finally towards an earth pit, right? Finally towards an earth pit actually. Okay, so these are only the three components uh, of our lightning protection system. Fine. So just let's enter into the basics. Okay. So what is a lightning arrestor? Sometimes we call it as like a surge arrestor also, right? So which is a device installed in order to protect the buildings, not just for the buildings. We have this lightning protection for the other structures also, like for power systems, the conductors, transmission towers, etc. So which is used to protect the buildings as well as the electrical power systems and equipment from high voltage source, which are caused by lightning strikes, right? Cause might be building, okay, fine, we are providing this kind of air rods or lightning arresters. But what about the case in case of power transmission lines? So that's not an issue because you might have seen one common cable or one common conductor that would be running on top of all the other phase conductors. Okay, hope you might have seen that, or if you have a chance, you can just check out that one, right? So that we call it as like a ground wire, so which takes care of this lightning protection system. Similarly, in case of this pole-mounted transformers, you would have seen on top of the pole, right? Like that would be a surge arrestor or a lightning arrestor. So that has to be grounded. So which has to protect our transformers. Similarly, in case of substations, also in order to protect the transformers and other components like our circuit breakers, isolators, current transformers, or potential transformers, we need this lightning arrestor. So the ultimate purpose is nothing but in order to safely drive the immense electrical energy. So huge amount of electrical energy, right? So around it would be like something around 100 kiloamperes or 200 kiloamperes it would be. So that should be discharged into the ground. So then we have to prevent the potential damage to structures and sensitive electrical systems. Okay. And in case of data centers or if any components if it deals with electronics, in that case cause electronics are more sensitive, so we have to install the surge arresters in their respective dbs. Like if it is a data center, we'll be using a udb, the usual supplies through ups, right? So we call it as a udb, ups db, and inside that ups db we need a surge arrestor. Maybe the lightning might be striking the exterior of the building, but still it may affect the interior part also. That means cause these electronic components are sensitive, so we have to install this surge arresters. So this is what it is like. Not all the time your lightning is going to strike the buildings, right? So at that point of time, what is the purpose of this lightning arrestor? Like might be not in the building, okay, maybe in the power system. So under normal conditions or under regular conditions, we say, I mean, whenever there is no surge or whenever there is no lightning strike, at that point of time, this lightning arrestor, it acts as an insulator. Okay, just acts as an insulator, and there won't be any connection actually between the conductor and the ground. No connection. Okay, just idle it is fine. This is going to act as an insulator. That's it for the conductors. So this means that the electrical system, it runs normally without interference from the lightning arrestor. But whenever a surge occurs, then this air rod or the lightning arrestor or this lightning rod is going to take an action actually, right? It's going to take an action. That means whenever a surge is detected, the arrestor, it quickly responds by reducing its resistance. So first of all, we have to understand that this lightning arrestor, which is not going to attract the lightning strikes, okay, which is going to just intercept. If in case the lightning is going to strike our building at that point of time, this is going to intercept, okay, intercept that surge, and it would be discharged safely with the help of down conductors towards the earth bed. That's what it is. So it's going to reduce its resistance, and anyway, it's going to create a low resistance path to the ground. And then we have divert this surge. How the surge would be diverted? Through this down conductors. That means the down conductor should be capable of low resistance, should have a low resistance path actually. So that's going to divert the surge or the lightning strike into the ground, safely into the ground, right? Okay. So for that, we need a normal earth pit, as we discussed in our last class during earthing, the same earth pit, but we use it for lightning system. In that case, that's going to become a lightning pit actually. Fine. And then returning to normal. So once the surge passes or it has been diverted towards the ground, and in that case, once again, it acts as an insulator. That's it. Okay. Once again, it's going to act as an insulator actually. Fine. So that's how the lightning protection system it is. So we have different types. We'll discuss these different types, and maybe I'll show you I mean, some other types of, I mean, the main components of this lightning arrestor system. So these are the different types of arresters we normally use. Like we have a rod gap arrestor, expulsion, wall type, metallic oxide, varistor, etc. So what is this rod gap arrestor? So they should be installed, like might be installed on a rural power line pole. So if you just travel through the rural areas, you might have seen in the power lines, right? So this is like a cost-effective option, and the best production would be required. Then we used to install these expulsion arresters. What is this? They're often found in substations, okay, little for higher voltage or higher current rating, so with medium voltage equipment, and hence anyway it's going to protect the transformers and switchgear, right? Cause all the costliest components that would be installed in our substation. And in case of substations, maximum, like we have external substation. If it is an internal substation, then okay, fine, like would be providing a lightning arrestor right above the on the top of the roof. So where does this lightning is going to strike? At the highest point, right? You're going to install at the roof, and if there is a chimney, a kind of a doghouse or something like that, so whichever is the highest point, so there we have to install this. And yeah, let's calculate like how many number of rods also would be required. Fine. So for substations, it's must like, and anyway, this external substation, all the components are exposed, right? It's clearly exposed. So your lightning is going to directly strike on it, right? Cause all our, I mean, the power system it is. So it's going to directly strike it. So uh, heavier protection is required. That's why we use expulsion time, which is far better than this rod gap arrestor it would be. And then we have valve type arrestor. So they are also installed in large power stations, substations, power stations in the sense like, in case of our generating stations, etc. Okay, generating stations, whatever the generating station it may be. So there we require. Okay. So good evening, Mr. Tony. Just now we started with this lightning arrestor. So just we are discussing about this lightning arrestor types. So there is a rod gap arrestor which we use in rural power lines, and then we have this expulsion arrestor normally used in case of substations. For what purpose? Like in order to protect the transformers and the other switchgear components, which includes or circuit breakers, isolators, and then yeah, and then we have I mean yeah, good evening. So then we have CTs and PTs. That means current transformers and potential transformers. So it has to protect all these things. Okay. And expulsion, yep. And valve type arrestor, similar. Like we use it for larger power stations, like generating substations. It may be a hydel power plant or thermal power plant or a solar power plant, wind power plant, whatever it is. So we need a valve type arrestor over there. So which is going to protect the surges caused by both lightning and as well as the switching surges. There is another thing called switching surges. Due to change in frequency or change in the voltage level or the fluctuations, there would be some kind of switching surges also. So there is a difference between these lightning surges and switching surges. Lightning is like, yes, quite by nature it is. Switching, yes, of course, due to the power system instability or the failure, the switching surges will occur. And then we have a metal oxide varistor, we say arresters. Okay, all are made up of different types of metals, actually, like zinc. metal it would be made up of, okay, for higher resistance purpose. I'm sorry, a lower resistance purpose, because whenever the surge current is passing through these kind of arresters, it should provide a low resistance path, right? If in case if it is having a higher resistance, then it would be a problem. Why? The surge current would not pass through it. So it should be having a low resistance path actually. And normally there's MOV, we say, like a metal oxide varistor arresters. We use it in residential areas. So which is going to protect the homes from surges in the main electrical panel. And then, like there are few some other arrest types of arresters also. We have a multi-gap arrestor, secondary arrestor, and a station class arrestor and a distribution arrestor also. So what is this multi-gap arresters? They are often again like it would be found on high voltage transmission lines, especially in industrial or any utility applications. And in case of secondary arrestor, we install at the electrical panel of a home. Okay, the secondary arresters. So which is going to protect the electronic and as well as the household circuits. And in case of a station class arrestor, they are going to be installed in large substations or on transformers. That means whichever is supplying power to industrial complexes. Like you might have seen a few industries with 33 kV, 66 kV, like heavy industries, right? So where a significant surge protection is required, or else it's going to damage the entire switchgear component. So there we need a station class arrestor. And distribution class arrestor would be installed on utility poles, the normal utility poles, like maybe just when we get outside of our home, you'd be able to find the transformers, right? Like the pole mounted transformers, etc. So there would be able to find this class of distribution class arresters. And it's going to protect, of course, the transformer is going to be the main component. So usually this would be installed in distribution substations in order to protect the transformers, right? So lightning arrestor is nothing but which is going to protect the equipment and protect the building, the external part. And in case of buildings, in case of our MEP works, we're going to protect the building. And in case of substations, yes, it's going to protect all the switchgear components, including the main part is like transformer. Then fire hazard prevention also, like there is usually a fire hazard risk, right? So that would be there. And cost savings. Okay. Maybe for our residential homes, like we are not dealing or we are not doing this lightning arrestor works. Why? Because it's a rare thing, but still, like wherever it depends upon the climate, vulnerability, weather conditions. Like might be few places they might be receiving heaviest rainfalls like throughout the year. In those cases, like we have to make do a research, like what would be the number of thunderstorms or I mean the rainfall capacity, etc. So depending upon that, it's a good thing. Like if you install this lightning arrestor, if in case if you don't have it also, like for example, if you have installed this solar panels, and it's a good thing to install a lightning arrestor over there. Why? Because there is a chance due to the solar panel, maybe the lightning surges might strike at that particular point also. So that's the reason. Like if you have any equipments in the roof, like motors or solar panels, maximum would be like solar panels for residential purpose. For industries, it's a must. Okay, cause it's business. Like you know, they're going to lose their business if in case everything got collapsed due to this lightning surges. So they have to install it. And one more thing, like if you have any a nearby building, like a taller building than our building, in that case, okay, if they have installed it, okay, it's not an issue if we have not installed it. Why? Because this lightning strikes, they are going to strike at the highest point only. That's the basic thing actually. Rare cases it may affect, but still it's going to affect the tallest part only. If in case it affects the tallest building, might be a nearby building also might get affected. That's what it is. Okay, so it's better to provide this lightning arresters. Even in case of Middle East countries, we are providing this lightning arresters. Whether there is no rainfall at all, but still we used to provide this one. And cost savings in the sense in the near future, if in something happens, if in case some incident occurs, in that case, it's going to save the cost, save the life, save the building too, save the business. But there are some disadvantages. Is nothing but the installation cost is high. Of course, the installation cost is there, and that we can't do anything about it, right? So that we have to install. Like that depends upon the type of the building, and we look into it what it is, and then regular maintenance would be required. Like that's the purpose we used to provide the test link also. Okay, the test link should be provided along the down conductor, and then a limited surge capacity. This depends. Like what is the type of level of protection we are providing. Like actually, there are four levels of protection, like level 1, level 2, level 3, and level 4. Level 1 in the sense the highest type of protection. So maybe more number of lightning arresters arresters would be installing it for the safety purpose. And level 2 is also similar to like level 1. Level 3, level 4 for normal purpose, like with minimum number of lightning arresters. Okay. That may also protect the building if in case damage occurs, a mild or a slight damage would be occurring. Okay. That's the only thing. Fine. So here, this is what like with respect to different applications we use, right? So like in residential buildings, in homes, yes, of course, we are installing it to protect the household wiring and sensitive electronics. This is most important, right? Like TVs. Anyway, we might think that that's an external surge, but still, that surge could affect our internal components also, right? Like TVs, computers, and all, whichever is an electronic component. So it's better to install a surge arrestor. That would be a good thing. And telecommunication towers, of course, it's a must because the tower's height, and of course, it's going to strike a telecommunication tower. So that should be, uh, provided with the lightning protection system. And because they are at high elevations, as I told you, these lightning surges, they want to strike the highest point only. And in case of power stations and substations, of course, it is required, like all our power producing components. So there's a high chance your lightning it's going to strike that particular transformer or any other switchgear equipment. So we have to install it over there. Like substations, transmission lines, everything has to be protected. Okay. And airports, yeah, of course, like a public area, like which works under radar systems, right? So control towers and navigational aids. If something has lost, all the signal would be lost. So this is a very, very priority. A top priority has to be given to this kind of airports or any other railway stations or like commercial buildings wherever there is a lot of public movement. Okay, so there we have to provide this kind of lightning protection system. And industrial plans, yes, it's a must, right? It's a must. Like generally comes in the scope or the specs itself. Okay, we have to provide it over there. Like a lot of machineries are there. It's indirectly which is going to affect our business. So we have to provide this lightning protection in industrial plans also. Okay. So where do we install this one? It's nothing but in the rooftop and high points of the building, right? In the rooftop or high points of the building. Like if, as I told you, if you have a chimney in the roof, or if you have something like a doghouse kind of thing, so that the topmost portion we have to install. And near electrical service panels and transformers, like for the external purpose, for the outdoor, right? Because for if it is your substation is like an indoor substation, then fine, we are going to install a lightning arrestor at the roof, which is going to take care of it. But still, in case of external substations, yes, of course, we have to provide this lightning arresters and nearby the transformer itself. And for transmission and distribution poles, it's mandatory. For communication towers, yes, of course, they're going to be taller, right? The elevation is too high, so we have to provide that one. And for industrial and chemical plants, because it's known if it is going to strike, the thing is there is a chance of fire, right? There is a chance of huge fire also. So that's the issue, like with this chemical or oil, gas plants, etc. Definitely, we have to provide this lightning protection system. And finally, yes, of course, in case of residential buildings, it won't be that mandatory in few places, but still, it's all for our own safety. It is right. So we can provide a lightning protection system actually. So before proceeding to this problem and few more details, let me show you like clearly like few details about this lightning protection system. So as you can see this, right, just a minute, I'll share it. Yeah. So as you're seeing it over here, these are the lightning protection materials, what I'm showing you, right? So these are the lightning protection materials. So like, which is going to include the lightning arresters, right? These are the arresters. We call it as air rod, lightning rod, or lightning arresters in any name. And then this is the lightning rod, okay? And then we have the down conductor. This is what a down conductor we call. Like usually it would be 25 by 3 mm, 25 in width, 3 mm is the thickness, okay, which is going to carry that surge current. And then we are grounding it, like earthing it with the help of an earth pit. So if I'm using this earth pit for earthing, then that's for earthing purpose. The same earth pit only. We have to install the earth rod as we discussed in the last class, the same thing. But if I'm using it for lightning, we call it as a lightning pit. That's it. We call it as what? Like a lightning pit. So here the resistance could be up to 10 ohms also, cause a huge amount of current or the surge. Okay, it has to take care of it, right? 100 kiloamperes or like 200 kiloamperes, it would be usually. And this is again an air rod, right? Okay. So this is how the system, like here you could see this. These are nothing but like usually at the corners and at the top of the point of the any top point of the building, right? Like the kind of a doghouse, yes, we have a lightning arrestor. Here we have a lightning arrestor. And of course, like in the corners, okay, like in almost all the corners, we need this lightning arresters. As I told you, it may not be required at this point, cause like we have a taller building when compared to this smaller building, right? So it may not require, but still for an additional safety purpose, cause like if in case the lightning is going to strike this point, so it's going to affect the entire thing, and there are like tanks also, right? So everything has to be protected. So maybe we can provide it like as per the calculation. We have a calculation. So like we have to collect the entire collection area. We have a formula. So as per that collection area, that divided by 360, so we can find the number of rods. Then I'll show you a sample problem. Okay, we can calculate the number of rods. And this down conductor is nothing but just you can use a 25 by 3 mm, and it depends like how many ever rods we have installed. Yes, so that much length would be required. Like that we have to just directly measure the length of the building, and including like if there are some equipments, as you can see, some AGO equipments, are ducting or motors, pumps, whatever it is, or water tanks. So like metal, if anything is of metal, everything has to be bonded, okay, with this lightning protection conductor, right? Each and everything should be bonded with this lightning protection conductor actually. Okay. And then the final earthing has to be done, right? We may use different pits, not like everything together. We are just discharging it towards one single pit. Better than that, like should have multiple pits, and we can interconnect all the pits also. If in case one of the pit fails, then another lightning pit is going to take care of it. So this is how it is. Like this is an external lightning protection system with a PVC sleeve. Usually, for the building aesthetic concern, it would be installed along with the in the construction phase itself, stage itself, right? Along with the steel we can install. But here, if you have missed it out and if you're installing it later on, or as per the additional scopes or something like that, in that case, it should be a PVC protected sleeve. Usually, the lightning conductor would be a bare copper tape. It is like which usually comes in a roll, like of around 50 meters roll we used to get. Okay, so bare copper we used to install at the roof area and the parapet walls, etc. But when it runs through the building, if it is exposed, it should be provided with a PVC sleeve, as shown in the drawing, right? As shown in this figure. PVC sleeve actually. Okay, this is like one of our project that we did in Qatar actually, and here we have a test link, and then it's connected to the earth pit. Okay, that's how it is. So the same thing over here. Like these are the lightning rods, a down conductor, or we call it as a main conductor, then connected to the ground. And you could see the supporting materials, like this is what that PVC down conductor, okay? But in case of the roof, the open area, yes, it would be going to be a bare copper tape only, okay? It's going to be a bare copper tape. And then this is a lightning arrestor. These are the earth rods. And this is like a square clamp actually, okay? Where do we use for connections, for different connections of your down conductor? Like we are bonding it to, the metallic equipments also, right? Like AHUs or whatever it may, all mechanical equipments. So we need this square clamp for bonding purpose, and rod to tape clamp. Okay, we have got this tape clamp also finally while earthing it. Okay, or else we can use an earth bar itself, as I showed you in the earthing chapter. We can use this earth bars also, like this, right? This is earth bar, and this is a normal kind of a saddle, a square DC clamp it is. So like at regular intervals, like 50 meter or maybe around 100 centimeter interval, we can install this uh DC tape clips, we say. Okay, like usually we call it as like a DC tape clip. It is like saddles how do we install for the conduits, right? For the support purpose, similar to that. Okay, so these are the main or major materials that we use along with the earth pit, right? Earth pit, it'd be like a square type, usually a concrete pit, right? So there is a principle called a rolling spear method, okay? Like this one, actually, the suppliers were supplying, all these materials, or the vendor. So they have a kind of a simulation software. So practically, this is not possible. So how to find out like which area is protected or which area is not protected in the building? For that, what they'll be doing is just they're going to roll a spear over the building. Okay, especially for irregular shapes of the building. If you roll over the building, what happens? Wherever the spear touches, okay, so that point is like not protected. That means there we have to provide a rod. Okay, I mean air rod or a lightning arrestor has to be provided. Whichever comes, like if I shown you over here, right? If it touches over here, yeah, here a rod is required, here a rod is required. But in this area, okay, in this area, like between these two areas, so this area we consider like it's protected. So there's nothing but maybe to clearly show you, if you just roll over the, if you just roll over roll over the spear over a building, like irregular shape of building, like, or in case of substations, etc. If you're rolling it over, practically we cannot do it. Okay, it's going to be a huge spear actually. It's like just a simulation software. So just if you roll over the building, wherever the spear touches, right, like this corner, this corner. So at those places, yes, of course, we need a lightning rod. Okay, we need a lightning rod or an air rod. And the protection area, this is the protection area. Okay, whichever wherever the spear covers the two parts, right, from wherever we have installed the rod. So this particular area here, we don't need any air rod over here. That means which is a protected zone, okay, which we call it as what, like a protected zone actually. So the spear rolls up over and over all the lightning mossa, whatever is included in the substations, and it can provide the lightning shielding actually. Okay, so a piece of equipment is said to be protected when if it remains below that curved surface, as I showed you, like this surface. So here one rod, here one rod, it touches the building, but here it doesn't touch, right? So that means this area we consider to be like a protected zone. Okay, just a simulation software it is. It's not like 100% guarantee, but still, like this is the procedure. Like a rolling spear method is what we follow for this lightning protection design actually. So as now you can see this, right? So this is like the levels of protection. We have four levels, like class 1, class 2, level of lightning protection system level we say. Okay, class 1, class 2, class 3, and class 4. We have four classes. And if it is like class 1 is nothing but we are providing a highest protection. Okay, the best protection. Class 2, the next. Class 3 and class 4 for normal residential buildings or general commercial buildings, we provide this class 3 and 4 protection. So what is that? It's nothing but we are going to roll the spear over this building, right? By a rolling spear method. And in this case, the rolling spear, right? For that, the radius is considered to be 20 meters only. That means if I'm going to provide this level 1 protection, okay? If I'm going to provide level 1 protection, then it's going to be just 20 meters only, right? 20 meters only. So what it means? It means like a more number of rods would be required. If it is 20 meters, this mesh, okay, it forms a kind of a mesh we say. So this mesh size, like all these are nothing but the down conductors, okay, so this becomes like almost like 5 meters by 5 meter. I need a mesh. So this down conductor here, it's 5 meters, here it's going to be 5 meters, okay, like 5 meters by 5 meters. So I need a down conductor also, I mean down conductor, and then a rod also. So the cost is going to get increased, but the level of protection is high. I mean the safety, with respect to safety aspect, this is very high. Like usually for industrial buildings or hi-fi, I mean for IT companies or whatever it is, wherever we are running the business, okay, fine, we can provide this level 1 protection. Similarly, when it comes to level 2, the roll, I mean the spear, what we are rolling over, we consider up to like 30 meters radius, right? 30 meters radius, slightly relaxed. So that means the mesh size, this size, okay, it'll be like 10 by 10. Okay, so maybe to some extent I may be able to reduce the down conductor as well as the lightning rods, right? I can decrease the numbers. And for level 3 and level 4, level 3 it's like 45 meters we consider, slightly relaxed completely, like 15 by 15. Okay, the size would be like 15 by 15, the mesh size. And in case of class 4 is the least level of protection, is up to 60 meters. Maybe just with 4 rods also I can just complete this building, this entire building, right? So that means 20 by 20 meters each mesh would be, okay, like 20 meters by 20 meters. So only minimum rods would be required, and my down conductors capacity, I mean the quantity also is going to be less. Okay, so these are different levels of protection. Like for whatever projects we are working on it, like just we have to check with respect to the specifications also. Like it depends upon the building, like building type, what application it is, for what purpose it is. Okay, then we have to decide upon these levels of protection actually, right? Then these levels of protection. So that's what is shown over here. Like if it is of LP1, 20 meters radius, the rolling spear we consider, and LP2, like 30 meters we consider. We exactly don't know like how this spear is going to roll over the building actually, but still this is an assumption. Okay, like level 1, yes, just 20 meters, it's going to touch the parts, and 30-meter radius. And level 2, and for level 3 it's going to be like 45 meters. And finally in case of level 4, yes, of course, like 60 meters we consider, completely relaxed we can say. So here this is the minimum peak current which your level 1, 2, 3, and 4 can handle. So if it is level 1 type of protection which can handle up to 200 kilo amperes, right? 200 kilo amperes it is. And level 2 up to like 150 kilo amperes. So the damage done to your building is very less. I mean the probability of lightning protection striking the building is just 1%. And if in case if I'm providing the level 2 protection, right, like which can handle up to 150 kilo amperes, in that case just 2%, okay, the level of damage to the building. I mean, if in case the lightning strikes your building, and in case of level 3, it's like 100 kiloamperes, which can handle 100 kiloamperes, a 3% probability. Here also a 3% probability. Both 3 and 4 are almost like the same kind of protection only. For less critical areas, for residential, etc., residential buildings or some semi-commercial buildings, yes, it's fine. We can provide level 3 and level 4 so that we can reduce the cost also, right? That means number of down conductors would be reduced, and as well as the number of air rods also would be reduced. And here it shows you the clear current ratings actually. So this level 4, if I'm providing the level 4 protection to my building, in that case, what happens? Like maybe there is a chance that up to 16 kiloamperes may strike my building. Okay. Like 16 up to 16 kiloamperes might strike my building. That means a small amount of damage would be there, right? And if I'm providing with level 3, there is a chance up to 10 kiloamperes, right? Up to 10 kiloamperes, and again a mild chance of damage to the building. Okay, there might be a damage to the building. But if I use level 2, a 5% probability, there is a chance that's going to damage your building. But if I'm using this level 1 protection type, then it's like just 3% probability, right? Where just 3%, a very, very a little damage that may occur. If in case it damages also, or else it's going to take care of it completely, no issues. Like all the lightning surges or the lightning strike, that would be completely discharged towards the earth, but still like a 3%. Okay, so that's the reason like we have to provide this level 1 or level 2 depending upon the complexity or the application of the building. Okay, that we have to decide it upon. And there is one more thing, like as you can see this in this particular building, like especially in case of this super story buildings, or what we say like skyscrapers, etc., there is a chance that your lightning, it may not strike only the roof, it may strike the building also, right? It may strike the building also. So where we have to consider this sort of thing, like if in case if your building height is above 60 meters and high, more than 60 meters and high, in that case, the topmost, like around out of 100% height of your building, like up to 80%, okay, not an issue. Your lightning is not going to strike. The topmost, rest of the 20%, okay, if it is like 100 meters, maybe 60, 80 meters, okay, like above 60 meters itself, we can start providing this down conductors. So what we have to do, like in the previous cases, if it is like just a normal building or less than 60 meters, just through the walls, okay, through the sides, corners, I can run the down conductors. That's it, with the help of this mesh. But if in case if it is above 60 meters, so what I have to do, like the top 20%, maybe 2 floors or 3 floors, whatever it is, again, all the entire floor should be protected with this mesh grid system. That means the down conductor should be installed over here. So if in case if there is a probability of your lightning to strike over this particular part of the building, maybe this floor or this floor, it's not going to strike it over here. It's going to strike the lightning arrestor only. Okay, then the arrestor is going to capture it. I mean, intercept. It's not observing it. It's actually going to intercept it and safely discharge it to the low resistance down conductor. Okay, so that's the thing actually. So this we have to make a note of it. Like if it is 60 meters and above, the first 80%, okay, no issues, no need to protect it. But the topmost 20%, it may be 2 floors or 3 floors. It depends upon the total height actually, right? It depends upon the total height. So we have to provide the protection. Hope you're clear with this one, right? So that's the basic concept actually. And there is a thing like as per IEC standards 62305, there is a table for lightning flash density. So while doing the calculation for this lightning protection system, there is an important term called lightning flash density. So for that we have a standard actually, like which is based upon the thunderstorm days per years actually, right? The thunderstorm days per year. So that we call it as a TD. What it is? The number of days in a year when thunderstorms occur in a specific area, right? And similarly, we have this lightning flash density that we call it as NG. What is it? The average number of lightning flashes, okay, per square kilometer per year. So this is the value that required. This lightning flash density NG is required for us. Like first of all, like we have to check whether exactly, maybe it's not such that for each and every building we need lightning protection. So first of all, we have to confirm whether our building, depending upon its height, whether it requires a lightning protection system or not. If it requires, then we have to proceed with the calculation. Okay. For that, this NG is going to help us actually. NG is nothing but the lightning flash density, which is like number of lightning flashes per square kilometer per year. Okay, per year. So like thunderstorms, this is like you can get it from some meteorological centers, right? Like if it is 10 thunderstorm per year, this depends again upon as per your geographical location, like wherever we are situated, right? It depends in the entire world. So if it is like up to 10, then the value is like 1.5, and 20 it's 3. So it increases as your thunderstorm, it increases. The lightning flash density also is getting increased. So no need to by heart this or something. Like if you want to do proceeding with the calculation, just you can refer to this particular table. And if it is like up to 100, maybe like 15 lightning flash density we have to consider. So by this itself, it's clear, like if it is 100 thunderstorms, yes, of course, a lightning protection is required, right? Of course, a lightning protection is required. And similarly, we have another reference table also. This is as per IS standards 2309. We follow this one. And with respect to thunderstorm days per year, and here it is like lightning flash density. So thunderstorm in the sense is a rare thing. Maybe whenever it rains, like during the monsoon season or a rainy season, at that point of time, might be 30, 40 maximum, right? Might be in your area. Just you can have a check on that one also. So it starts with like five numbers, might be one or two in case of these Middle East countries or hot and humid places. There is a chance. Okay. Like 5, 10, 20, 30, 40, 50, 60, 80, 100. And for each and every, for thunderstorm value, yes, we have got this lightning flash density, like 0.2 flashes to ground. That means nothing but the flashes towards the ground. Okay. There's a probability just 0.2 in case of just 5 thunderstorms, like hot and humid places. And in case of 10, like just zero point 0.5 only is required. 20 means 1.1, and 60 means like 4.7, and 100 in the sense like 9.2. So as the thunderstorm increases, the days per year increases. Similarly, the lightning flash density is also going to increase. And then we have a factor also, depending upon the application of the structure, we have to apply these factors in the calculation too. So for normal house or buildings, it's just 0.3. Okay. And in case with an outside aerial, in that case, 0.7, there is an aerial, right? So the probability of striking, the lightning strike is high. And factories, workshop, or laboratories, so it's like 1. And for office blocks or hotel, yes, of course, it'll be little high, like 1.2, cause like it depends upon the height of the building, or everything is like a high-rise buildings, it would be. And block of flats or residence buildings, in that case, again, 1.2. And churches, hall, theaters, museums, exhibitions, yes, we should consider 1.3. And in case of department store, all this post office, etc., again 1.3. Then we have airport, station, stadium, again 1.3. Schools, hospitals, very critical, so 1.7. Okay. Whatever the structure it might be a smaller school or a taller with a high elevated school, whatever it is, but still little we have to check out for the safety also, right? Like that means at least 1.7, that should be the factor. And others, apart from these buildings, if any other structures, if you come to experience, then in that case, we have to use 1.2, right? 1.2. And similarly, based upon the type of construction, like whether it is a steel frame or reinforced concrete, usually without metal roof. This is nothing but with respect to the roof. Normal a concrete roof would be there, or else a metal roof would be there, right? Or else a masonry, a plain concrete or a masonry without metal roofs. So for each and every type of structure, okay, the construction type, we have a factor that we have to apply, right? So that we have to apply. So like steel frame, reinforced concrete, steel framed encased with a metal room, or a roof, or a reinforced concrete with metal roof, then a brick or plain concrete or a masonry without a metal roof. Like normally we used to construct this kind of building for residential purpose, etc. So I can consider 1.4. And timber framed or clad with metal roof. In that case, nothing. Okay, no need to consider. But for a plain concrete or masonry, yes, we have to consider. It would be like 2 actually. Okay. And the consequential effects for that also, we have some factors, like it again depends upon the building types, right? Like we have domestic or office buildings, factories or workshops, industrial and agriculture buildings, power stations, telephone exchange, industrial key plants, historic buildings, museums, art galleries, schools, hospitals, children's homes. For each and everything, as per the factor, just we have to have a look on this one. Depending upon the criticality, the value is going to increase, right? As you can see this, the value increased. Fine. So these things just you have to check with these tables. That's it, while doing the calculations. Okay, but nothing to keep in mind, etc. Just you have to. I mean, no need to buy out all these things. Just you can check it out. So degree of isolation, how much it will be, like structure in a large area having greater height. In that case, 0.4, and structure located in area of the same height, 1, and structure completely isolated. In that case, a factor 2 has to be applied. Okay, fine. So just we'll check with a calculation, an example. like calculate whether a lightning protection is required or not for the following building. Okay, so now just calculate the number of down conductors, and maybe we'll calculate the number of air rods required also. Okay, so let the length of the building be 60 meters, too long, right? Okay, fine. Width of the building is almost like 28 meters. The height is like around 23 meters. It is okay, 23 meters. Fine. Now the lightning stock flashing density has been provided over here. Number of thunderstorm is like 80 days per year. Okay, like 80. Then what would be the lightning flash density if you refer to the previous one? Okay, like if it is 80, here it's shown, like if I'm referring to this particular standard, IS standard 2309. In that case, for 80, how much it is? It's 6.9. Okay, it's 6.9 from the table. So it's not 69 actually. Okay. Uh, just a minute, I'll show you. It's not going to be 69. Actually, this is 6.9. Okay, this is 6.9 kilometers square per year. Okay, just a small change, a small correction. It's not 69, just a typo error over there. So, what is the application of the structure? It's going to be a house and buildings. Okay, and type of construction. So, these are nothing but these factors we need. Okay, whether I mean, while checking whether a lightning protection is required or not, we have to check all these factors as I showed you in the table. So what are the factors? Like we have the first thing is NG value. This is what most important, right? There's lighting flash density. This is what required. And then after that, like depending upon the building type or the application, like the application of the structure is like a house and building fine that we call as like A. Type of construction is going to be like a steel framed, right? Encased without metal roof, and contest or consequential effects like a domestic or usual normal office buildings, and degree of isolation is what? A structure in a large area having a greater height. So we are considering this one. And type of country, like a flat country at any level, like up to sea level or whatever it is, we are considering it. So there is a standard. The overall acceptable risk factor should be 0.00000001. Okay, so if it is less than this value, then a lightning production is not required. But if it is greater than this value, then lightning production is required. Okay, no need to get confused with this one. I'll show you in the calculation how it is. Hope then you'll be understanding this well. Okay, right. I'll show you that. Yeah. So the first and foremost thing we have to do the thing is like we have to find a thing called collection area. Okay, we have to find a thing called what? A collection area. So collection area in the sense like wherever the lightning may strike, wherever there's a probability. So in order to do that, this is the formula. There's a basic mathematics only, which is given by length into width of the building. Okay, plus 2 into length into height also. We are considering the length into height also, plus 2 into the width into the height also. Okay, length into height, and as well as plus 2 times the width into height also, like all the perimeters we are considering, plus 3.14, that is your pi into h square, like a 360-degree. Okay, like the height square it is. Fine. So length is 60 meters, width is 28 meters, and what about the height is 23 meters, right? 23 meters. So we have to substitute all these values, like length is 60, width is 28. So multiply it with plus 2 into 60 again into 23 is the height, plus 2 into width is 28 and height is 23, plus pi is 3.14 into height is almost like 23 into 23, right? So the collection area would be 7,389 meters square, right? If we substitute, this is the main formula, just you can remember this one. So we are considering the overall building. So what we are calculating here, the total collection area wherever the lightning may strike, right? Wherever the lightning may strike. So this is going to be the collection area, which is around 7,389 meters square it is, okay? Meter square. And now the probable number of strikes to the building is given by this particular formula. It's nothing but AC is in the collection area. So that should be multiplied by Ng. What is this Ng? The flashing lightning density, right? The flash density it is. So that into 10 power minus 6 numbers per year. So we got 7389. That multiplied by, what is it? 6.9. It's not 69. As I told you, it's a typo, right? 6.9 into 10 power minus 6 numbers per year. So you'll be getting 0.05098 numbers per year. Okay. 0.05098 numbers per year. Okay. So once after getting this probable number of strikes to the building, and now what we have to consider, like we have to consider all those factors as I showed you. It's nothing but just you have to refer to the previous tables. That's it. Okay. Now hope you'll be understanding why we need all these tables actually, right? Why we need all these previous tables like these things, like with application of structure, with respect to the type of construction, then with respect to the consequential effects, and finally the degree of isolation. So all these things to be considered for that particular type of building, everything that has been provided. Okay, the data has been provided. And in this case, like what are the multiplying factors? Like A into B into C into D into E. A in the sense application of the structure is the house or the buildings. And as per the table, the multiplying factor is how much? 0.3. That we are getting it from the table. Similarly, the type of construction, it's going to be a steel framed encased, right, without a metal roof. That means multiplying factor is going to be 0.2 from the standard or from the table. And the contests or consequential effects, so that's C, which is given by domestic or office buildings. The multiplying factor is how much? 0.3. So we're doing it for a domestic or official building. That's it. Either a residential or a semi-commercial building it is. Degree of isolation D would be like structure in a large area having greater height. So for greater height, it's going to be like 0.4 is the multiplying factor. And finally, the type of country E, which is a flat country. So the multiplying factor is 0.3. Everything, all these details, we are getting it from the table as I showed you previously, right? All the details are there. And this flashing density is also available. So the only thing what we have to do is like we have to just calculate this collection area, right? We have to calculate this collection area. So after getting this collection area, just multiply it with the lightning density, right? Lightning flash density into 10 power minus 6. We'll be getting a value. And then just calculate this overall multiplying factors. That means just apply all these overall multiplying factors with it. Okay, overall multiplying factors with it. And finally, if you multiply all these things like A into B into C into D, 0.3 into 0.2 into 0.3 into 0.4 into 0.3. So that would be like 0.00216. So this is the overall multiplying factor. Okay, this is what the overall multiplying factor. And now what we have to check is like the overall risk factor. So what is this overall risk factor? It's nothing but whatever the total multiplying factor we got. How much? It's 0.00216. And that should be multiplied with the previous one, with the collection area that we have multiplied with the lightning density, flash density, right? With that, we have to multiply. So 0.00216 should be multiplied with 0.05098. So I would be getting 0.000110127, right? So, and now what we have to do? Now, like we have to calculate the area and the perimeter of the structure. Okay, area, as you know, length into width. Simple mathematics, right? So A into B, that would be 16 to 28. 60 meters is the length and 28 is the width. So it's going to be 1680 meters square. Okay. And what about the perimeter? 2 into L plus W, right? 2 times your length plus width. That's your perimeter of the building. So 2 into 60 plus 28. So that's going to be like 176 meters. Okay, 176 meters. But now let's confirm one thing. This is required for the further calculation. I mean, what we have to confirm is whether a lightning protection system is required or not, right? So up to what range it is not required? I mean, if it is like less than 0.0000001, that means 10 power minus 6, right? So up to that range, we don't require. But this is like this value slightly greater than this because after 3 zeros itself, we are having 110, right? 0.0001 it is. Here it is 0000. So that means this value is greater than this value, right? So what it means, like the calculated overall risk factor is greater than the maximum acceptable risk factor, as I showed you in the previous case. Okay, if it is greater than the maximum acceptable overall risk factor, this one, in that case, a lightning protection is required. Of course, it is required for this building. If it is not required, means this value should be less than this. Okay, it should another 230 should come over here. Anyway, this is going to come. Okay, anyway, it's come. Fine. And now we can calculate the number of down conductors. So how to calculate? So the number of down conductors is given like as per the base area of the structure. Base area in the sense, this is the formula. Just few formulas you have to remember. The first thing is like the collection area, then multiply it with the lightning flash density. And the second, just area and the perimeter. Okay. And then like the down conductors. What is this down conductors as per base area of structure, which is given by 1 plus AB minus 100 by 300. What is this AB? That's nothing but your area. Okay, 1 plus area minus 100 by 300. Standard formula, that's it. So which is equal to 1 plus 1680 is the area of the building, length into width. That minus 100 by 300 will be like 6 numbers. And with respect to the perimeter of the structure is equal to P by 30. What is P? Perimeter. How much perimeter we got? 2 into L plus B, right? So 2 into, 60 plus the 28, length plus width. So it's 176 divided by 30. Again, like 6 numbers, right? So the minimum number of down conductors is going to be 6 numbers. And finally, finally, the lightning protection is required. That's what we have analyzed from this one. And how many down conductors required? As per the base area, we need six numbers, or as per the perimeter of the structure, we need six numbers. So you can depend whichever is maximum that we have to choose. Here is like almost both are same. If in case as per the perimeter, if I'm getting seven, or as per the area, if I'm getting seven or eight, in that case, the large in number that we have to choose. But here, the minimum number of down conductors should be at least six numbers. So this is with respect to the down conductor. But actually, if you want to calculate uh, the number of down air conductors, the number of air rods required. So what we have to do in that case, like as I'll show you, like here we have calculated a thing called total area, collection area, right? So as you can see, this AC. So this collection area is required. How much it is? It's like 7389, right? So we are getting 7389. So in order to get the number of lightning arresters or number of lightning rods, which is given by the total collection area, this AC by 360, like total 360 degrees we are saying. Okay. So how much is AC now? 7389. That divided by 360. So if you just calculate this one, you would be able to get that value. Okay. You'll be able to get the total number of rods actually. So how much will be getting it? Like just let me calculate this one. So it's 7389, right? 7389 divided by 360. So almost 20.5, 20 to 21 rods are required. Okay, lightning rods are required above this building. That's what it is. And if your collection area is smaller, yes, minimum number of rods. And all these rods you can install like usually in the corner of the building, right? Usually we can install at the corner of the building. Okay, this maybe just I'll include it, or else I have a separate lightning calculation for another example. And all these things like you'll be receiving it. Okay, you'll be receiving it. That's like from my calculation. From my projects that I'll send you. So, like with respect to the level of risks, okay, already we have discussed this one, okay, with level one protection, level two protection, level three, and LP1. That means the lightning protection level one is going to be the highest level of protection, and LPL2 is going to be the medium, LP3 low level, LP4 the minimum, the least level. And as I showed you, the consequences also, the side effects also, like up to 16 kiloamperes that may strike your building if in case of the least protection. And in case of the highest protection, just maybe it may be if it strikes, it may be up to 3 kiloamperes only, right? It may be up to 3 kiloamperes. These are the things I showed you, like 200, 150, 100, and maybe 100 or 75 kiloamperes in case of lightning protection level 4. Okay, it may be that much. Okay. So like you'll be able to calculate this discharge current also in some cases. How we can calculate? That means the discharge current is nothing but which represents the amount of current the arrestor can safely handle. So there is a formula. IN is nothing but the discharge current is given by square root of 2 into U maximum by Z. So what is this Z? Z is nothing but the impedance of the lightning path, okay, which would be always measured in terms of ohms, right? If it is impedance or resistance, yes, we are going to measure in terms of ohms actually, and the maximum voltage of the electrical system, okay, and that's your Umax. So just an example, if the maximum voltage is 415 volt, like for our system, for our building, right, and the impedance is like 2 ohms, maybe you can consider 1 ohms, okay, 2 ohms, just a rough example. In that case, IN, the discharge current is given by square root of 2, that's 1.44, right, into 415 by 2. So that would be around 414.8 amperes. So this is going to be the maximum discharge current actually, right? So this is the value. This value is the required discharge current for selecting an arrestor. Okay. So this formula you have to remember actually. And there is one more thing called impulse withstand voltage. So what do we mean by this impulse? Impulse is nothing but the lightning arrestor, whatever we are selecting or choosing, it should be capable of withstanding the impulse or the surge voltages, right? Whichever is generated by the lightning strikes. So that we call it as an impulse withstand voltage, which is given by UC equal to K into U. So what is this UC? It's an impulse withstand voltage. K in the sense a multiplication factor, right? K is nothing but a multiplication factor. Normally, it depends upon the lightning arrestor. Like typically from 1.5 to 2, we can just check it out from the vendor or the manufacturers, right? Vendor or the manufacturers. And U is a normal operating voltage, right? Use the normal. What is the normal operating voltage? Is 415 volts, as we discussed in our previous classes, right? It's going to be just 415 volt. And the multiplication factor is going to be like 1.5. Okay, minimum. So just you have to substitute. You'll be getting the value 1.5 multiplied by the normal voltage 415. So this impulse withstand voltage like up to 622.5 your lightning arrestor can withstand. It may be the system maybe for 415 volt, but still the maximum voltage level your lightning arrestor can withstand would be of how much? Like around 622.5 volts. Okay, that much it can withstand. Right. So finally, we can choose the lightning arrestor based on the current capacity and the voltage protection. So the nominal discharge current, as I showed you. What is it? The arrestor should be able to handle the calculated value. An impulse protection level, just now we have seen, like the arrestor should withstand the calculated impulse voltage also. And the surge protection capacity, there's nothing but the arrestor which is going to offer the surge protection to prevent the transient voltage spikes. We have to look in with reference to that levels, different levels like level 1, level 2, level 3, etc., level 4, etc. So depending upon that, if you're designing the level one, then be sure like it's going to cost you more actually. But for critical applications, yes, we have to design that level one only. Okay, maybe some other calculations also like I'll send it to you like after. I mean, like maybe in 1 or 2 days, right? You'll be receiving this lightning and few earthing calculation. Like from my side, these are all like from, I mean, already available from Augmentech. You'll be able to get these things, but few other things like I'll be sending it actually, right? And there is one more topic pending. Like I think this we discussed a lot of times in the sense like along with the other topics. What are the other topics? Like when we discuss this MCC panels, hope you might be knowing it. Like usually in case of inductive loads we have a reactive load also, right? We have a reactive power also apart from active power. So due to this reactive power, what happens? The power factor would be lagging. So if it has too much lags, then the system is not efficient. Maybe like in case of industries, they might have to pay a huge electricity bill, and it may sometimes they may impose the fine also. Okay, the utility people. So they might be imposing a huge fines, penalties, etc. So in order to overcome all these problems, what we have to do, like we have to install the capacitor banks. Okay, we have to install the capacitor banks actually, so that which is going to compensate for that reactive power. As again, I'm telling you, like this reactive power, it cannot be ignored, right? It cannot be controlled at all. I mean, that would be existing. We can't do anything about it, but still we would be able to compensate. That means it's nothing but, for example, 20 kVAR. Okay, if that's the reactive power. So if in case if I'm not using any capacitor banks, so that 20 kVAR kilovolt ampere reactive that would be supplied by the utility itself. Okay, in that case, the system is not efficient. Instead of using 10 kilowatts, you might be using 15 kilowatts. That's the basic thing. So what we can do is like if I'm going to install the capacitor banks, if we are going to install the capacitor banks, in that case, maybe up to 15 kVAR, okay, I'm compensating it. Just 5 kVAR would be like, might be supplied by the utility. In that case, okay, fine. Like I'm going to improve the power factor as well as I'm not going to impose any, I'm not going to be impose any fines or penalties, etc. So I'm going to maintain that power factor. It's very important in order to for the efficiency also, right? A system, in order to, for a system to work efficiently, we have to increase the power factor. So there's nothing but the capacitors. Bank in the sense a collection of capacitors, either installing in series or parallel. Most commonly, like we used to install it in parallel only because these capacitors are always related to the voltage. As you know, voltage would be normally connected in parallel, right? A potential difference. And the inductors that would be like in series. That means along with your current. So a capacitor bank is nothing but which is used to improve the power quality. That means you're indirectly your power factor, right? Then it's going to manage the power flow, and moreover, which is going to increase the energy efficiency also. So that means bank in the sense consisting of multiple capacitors, which is connected in series or parallel in order to achieve the desired capacitance value or for the compensation of reactive power. That's it. So most cases it would be connected in parallel. Maybe in few cases might be in series also, but avoid the series connection. It should be in parallel actually. So power factor correction, that's the major thing. Why do we use this capacitor banks? And then it's going to reduce the voltage drops. This is again a thing. Why this voltage drop occurs? Because as the length increases, might be for any conductor or a cable, your reactance is going to increase, right? Resistance and reactance. If the resistance and reactance increases, the impedance, more number, I mean, the impedance indirectly is nothing but the impedance we say, the impedance increase. So if impedance increases, a lot of reactive power also would be involved in that one. That means that sine theta. Just remember, real power factor would be like cos theta, usually we used to say. And in case of reactive power, that's like denoted with by sine theta. Okay. and then reduce the losses in transmission lines. Of course, if you correct the voltage drop, I mean, if you're correcting the voltage drop or if you're correcting this power factor, automatically the losses would be reduced in case of a transmission lines, right? So, but there are some disadvantages also. Like, yes, of course, maintenance requirement is there. Then risk of over voltage sometimes if you are not designed properly, and high initial cost and space requirement. But disadvantage is nothing that bad actually. These are the drawbacks, but still we require capacitive banks. Okay, no need to consider these things. Yes, of course, an investment would be there in order to perform. A system has to perform. I mean, efficiently. Yes, of course, we need this capacitive banks. And where do we install these capacitor banks? Maybe like for small residential buildings at our home, okay, we don't have any capacitor bank because we don't have any, not much inductive loads. But in case of commercial buildings, yeah, some few pumps would be there, firefighting pumps or plumbing pumps. It may be required. Okay, it may require. Okay, and in case of industrial buildings, this is a must because all our machineries, which works with the help of AC or DC motors, right? So definitely, we need this, right? Definitely, we need this capacitor banks. And in case of power utilities and substations, also we need. Okay, in case of power utilities and the substations, very important. And in case of renewable energy systems like the solar systems, wind power, hydropower, etc. And data centers also. Okay, data centers, like rather than a capacitor bank, we have another thing called, I think I told you once, like we have a thing called active harmonic filters, right? So usually, in some projects, like in one of our projects also, rather than installing this capacitor banks, we have installed a thing called AHF. AHF is nothing but like active harmonic filters. So inside that harmonic filters itself, we'll be installing the capacitors too. That means, which is like for a dual purpose, we are using it, which is going to take care of this power factor correction, and as well as which is going to take care of, I mean, the harmonics also. Why harmonics? Because data centers, a lot of electronic components. I mean, all sensitive components. So wherever we have these electronic components, there is a formation of harmonics. Harmonics in the sense that if there is a change in frequency, yes, of course, electronics are DC, so there would be a change in frequency. So what happens? The voltage fluctuation. So that would be kind of a harmonics that would be present. So harmonics indirectly leads to losses, or this indirectly contributes to this reactive power. So we need this. I mean, active harmonic filters or the capacitor banks in case of data centers too, right? And hospitals, yes, of course. Too much of loads would be there. Like you might be using some specialized machineries like the MRI scanners or whatever it is, CT scanners. So each and everything, like they might be having certain harmonics. Yes, of course. Here also we have to deploy this capacitor banks. Okay. And this is a simple thing in order to calculate this capacitor bank, nothing much. So just a sample example, you can see this. So if we know the real power, that's it. We can calculate the reactive power. I think on one of the load calculation also I showed you. We have done a load calculation also, right? A load schedule in that we have seen this one. So the first thing is you have to determine the existing power factor. So usually there will be a power factor meter also in your industry or building or wherever it is along the LT panels. Okay. So we have this power factor meter, similar to ammeter, voltmeter, multifunction meter. With respect to all meters, we have this power factor meter also. Okay, so where we can check the power factor. If in case the reactive power increases, that means if all the motors are running at that point of time, yes, of course, the starting current would be high, and as well as the reactive power also would be high. So automatically, what happens? Yes, it's going to show a low power factor, but whenever the motor starts at that point of time, what happens? Automatically, this capacitor banks also are going to switch on. Why? Whatever the reactive power is available, the relay is going to sense it. Okay, the relay is going to sense it and automatically correct its power factor. That means it compensates for that reactive power factor, for that reactive power, right? So the first thing is like where to determine the existing power factor. So this is usually obtained from an energy bill or by a measurement, okay, through a meter, and then set the target power factor. What should be the target? One is like unity, which is not like practically possible. Only in case of some resistive loads, like only lighting and heating load, it is possible. But there also we don't consider one actually. Like in countries like Saudi, we go up to zero point 0.9, 0.95. Maybe in few other countries, like might be having some power factor also 0.8, 0.85, 0.85. We consider for design purpose usually. Maybe a few countries they still go with zero point 0.8 also. It's not such that we should not start all motors together. So yeah, the thing is like whatever the system we are designing it, like whether I'm going to design a transformer or whatever it is, like I'm going to design based upon like for example, if in case if I'm going to start all the motors, yes, of course. So I'll tell you. It's not the thing like that, maybe for some operations we may start all the motors also. Okay, if really there is a requirement, yes, of course we have to start. Or else, as you said, Mr. Tony, it's not required to start all the motors together. That might be a problem because a high amount of starting current and as well as the reactive power also would be too high. So that's the reason what we used to do. Let me tell you, for example, okay, like we were getting into this problem. Let me show you a few, like just a sample, okay? Like if I have a motor, okay, for example, if I have a motor maybe with 100 kilowatts, okay, maybe with 30 kilowatts, and another one with like 50 kilowatts, just an example I'm telling you, okay. So all these three motors would be having different reactive power. Okay, for this I would be sizing a capacitor, maybe like for example like 40 kVR, just an example I'm telling you, not the original calculation. And similarly for 30 kilowatt, maybe like 30, not 30, like maybe 10 kVR, okay, just an example. And for 50 kilowatts, maybe the capacitor value would be something around 20-25 kVAR. Okay, just an example I'm telling you. 25 kVAR. So what I'm going to do, like exactly we can't say that from each and every motor if I start, because some of the motors might be using different types of starters. Like if it is your pumps, like secondary pumps for HVAC, like I think you would have studied, they use VFD. If it is of VFD, the starting current is less, like just 1.5 times, right? 1.5 times, so that the reactive power produced also would be like less. And if in case of star delta starters is like 4 times, right? For some old like maybe a normal firefighting pump or a plumbing pump, I might be using a star delta starter. In this case what happens, the reactive power may be a little high, like starting current also would be little high, right? 4 times it is. And maybe I might be using for the lathe machines and all, I could use an auto transformer starter, that would be like 3 times your normal current or the full load current. So what happens, like if this is 40 kVR, we may not guarantee that only 40 kVR is going to flow. Maybe 30 kVR would be reactive power that would be flow at the time of starting, or maybe 20, or maybe above 45 also. So that's the reason, like what we have to do, we have to split all these capacitors like in a common capacitor panel. Rather than providing this, what I can do is like, for an example, I'll show you like a 20, okay, maybe here I'll show you. So whenever I'm installing capacitor bank, like a main circuit breaker, with the help of circuit breaker, and then I need a contactor. Okay, just inside the capacitor banks, we need a circuit breaker, and after that, we need this contactors. Okay, the contactors like a this is your CB or the circuit breaker, and then I have to connect it to this capacitor banks. This is the capacitors, right? The capacitor banks. So I have to connect it to the capacitor banks. So, like maybe few I'll show you. So whenever we are designing the capacitor banks, what we have to do, like rather than directly installing for these three motors, okay, just consider best these three capacitors, okay. So what I'll do is like maybe this I'll install a 20 kVAR, this may be 20 kVAR, like let this be 20 kVAR, 20, 40, 60. How much is our total kVAR? It's like 40 plus 10, 50 plus 25, like 65 it is, right? 65, now it's 20, 40, 60. Maybe what I'll do, still I can further split it like 10 kVAR, 10 kVAR. So 20, 30, 40. Let this also be 10 kVAR. 20, 30, 40, 50. Maybe one more capacitor bank. Okay. Let this be. Okay. Just a minute, I'll resume that. Yeah, now you're able to see this, right? So what I have done, like 20, 30, 40, 20, 10, 10, 10, 10. Okay. 20, 10, 30, 40, 50, 60, and maybe one 5 kVAR also. Okay. Like one 5 kVAR also. So what it does, like for all these three motors, I'm going to enclose in a single capacitor bank, Mr. Tony, Mr. Morosi, right? In that case, whatever the reactive power it is, like there would be a relay. Okay. This we call it as a active harmonic, I mean, power factor relay. Okay. Like automatic APFC panel we say, okay, automatic power factor correction relay we have. So this relay is going to sense, okay, the reactive power, and then it's going to feed to the circuit. That means depending upon the reactive power, for example, if it is any of the motor would have started, or if you start all the motors together, also not an issue. Like we have an automatic operation. Two modes of operation is available for your capacitor banks. Like one is manual operation, somebody has to switch it on, or automatic. Usually we go with automatic type. So in case of automatic type, that's with the help of the relay, APFC automatic power factor correction protection panel would be there. So what it's going to do, like if in case all the motors started together, then like stage by stage, okay, one by one capacitor, and that too depends upon the reactive power. If every of all the motor starts together, also we can't ensure or guarantee that this is going to be total 40 plus 10, 50 plus 20, 25, not like 75 kVR. Okay, maybe little less kVR also would be there. So depending upon that, these capacitors are going to start automatically on off. If in case my requirement is like maybe 70 kVR. If it is 70, then for 20, 30, 40, 50, 60, okay, maybe one more 70, and I'll include a 5 kVR also. Okay, I'll include a 5 kVR also. So a stage by stage it's going to start. Is it clear, Mr. Tony? A stage by stage, like whatever the requirement it is, it's going to start. So that's the reason, like we have to split this capacitors rather than directly providing for each and every motor. If it is 40 kVR, okay, 40 kVR capacitors available, but still is a good practice or a best practice to differentiate. I mean, what we can say, like split it. Okay, like we can split this capacitors, and if we install it, and as per the original requirement, it's going to get adjusted actually. Okay, it's gonna get adjusted. So this is how like we have to design the capacitor panels, right? This is how we have to design the capacitor. So this we call it as like 1, 2, 3, 4, 5, 6, 7, like a 7 stage capacitor panel. Okay, like a 7 stage capacitor panel. And one more thing, like along with this capacitors, what we have to do, there is one more thing that you have to remember, like whatever is our direct transformer rating, right? For example, if my transformer rating is like around 800 amperes, okay, 800 amperes, okay, not 800 amperes, 800 kVA, sorry. If my transformer power rating is 800 kVA, so 2 to 3 percentage a direct capacitor also has to be provided along with these capacitors, okay, just for a safer side. A 2 to 3 percentage a direct capacitor we have to provide along with this capacitor. That means a maximum like 3 percentage of 800 you have to consider. Okay, so how much it will be? Like 24, right? So it's going to be like 24. So this 24 kVR is required. So that means at least 20 to 30, maybe one direct capacitor. So like a 25 kVAR, okay? 25 kVAR direct capacitor. This we call it as a direct capacitor. This we call it as a direct capacitor. This also has to be provided along in your, I mean, in your capacitor bank. Just you can have a check on your capacitor banks also. Okay. So this is what the most, I mean, the common thing actually. So, but still we call it as a 7 stage only, because the direct capacitor we should not consider in this stage. Apart from the direct capacitor, we have 1, 2, 3, 4, 5, 6, 7. This depends upon your idea. You can just split it out. Okay. You can just split it out. So it's a 7 stage capacitor along with the direct capacitor. The direct capacitor just for a 2 to 3 percentage. 2 is minimum, 3 is maximum percentage of your the main transformer capacity. That's it. Okay. To your main transformer capacity, we have to design the things. Hope this is clear for you now, right? So whatever it is, if your motor starts together at a time, also not an issue, which is going to adjust it. Maybe another 5 to 10 extra kVA also you can provide, not an issue. Like 8 stage, 9 stage capacitor, that's not going to be a problem. Okay. So now let's have a look into this calculation. So first is like we have to determine the existing power factor. Fine, from the readings or from the energy bills we'll be able to get it. Then set the target power factor. It's going to be 0.9 to 0.95, maximum 0.95. It's not going to be 1 or unity. Is not possible practically. And then we have to calculate the active power. That means nothing but your kilowatts. Once you know the kilowatts, you can calculate the reactive power. So this reactive power is whatever the reactive power we are getting it, right? So that's going to be our capacitor bank size. That's it, kVAR. Reactive power would be always rated in terms of kilovolt ampere reactive. Okay. And active power would be kilowatt. Active in the sense the actual power which is consumed. This is like not the actual, this is like the useless power, but still it exists. We can't do anything about it, right? As I told you, we can't do anything about it. Okay. Usually in inductive loads or motor loads, cause in order to for that induction principle, a magnetic flux lines would be produced. Okay, then only the mutual induction is going to take place, and EMF, an electromotive force, would be induced. So that would be like, I mean, this reactive power is going to help that one. So we can't avoid it. Still, it exists. So we can compensate it, right? We are compensating it. So for reactive power, this is the formula. Your Q is given by P is nothing but the active power. Okay, the active power should be multiplied by tan of, okay, tan of cos inverse of power factor, right? Whatever the existing power factor, right? Cos inverse of that power factor. Okay, this PF is nothing but your power factor. That's your cos theta. Okay, so like then what you have to do? Then the fifth point is like we have to determine the required reactive power compensation. So what it is, just we have to calculate the required kVAR of the capacitor by finding the difference between the initial and the target reactive power. So there is a formula. There's nothing but your Q required equal to what was the initial power factor, maybe zero point 0.8 or 0.75, whatever it is, that we have to check. So that minus whatever is the target. Okay. The target in the sense like applying the new power factor. Is it zero point 0.9 or 0.95 to a max? Okay. 0.98 also in some cases, but practically 0.95 is a zero point 0.9 itself is a very good power factor. If in case if you're achieving zero point 0.9 itself, it's a great we can say, but still 0.95. Okay. Then we can select the capacitor bank size. Okay, then we can select the capacitor bank sizes normally. So just a sample example I'll show you, like an example calculation it is. Suppose for example, just assume that our active power is 500 kilowatts. Okay, 500 kilowatts maybe a motor, a load you can consider. And the power factor is like very low. Like we have taken a reading from the power factor meter, it's going to be just 0.75 only. So that means you assume like if instead of consuming this 500 kilowatts, maybe the actual power would be running up to 600 or 700 kilowatts actually, right? The kVA, okay, the kVA would be that much. It's nothing but just you can check it off. Like if 0.75 is the power factor, right? If 0.75 is the power factor, just you can divide that, right? So it's nothing but your 500 divided by 0.75. So it's like 666 kV kilowatts. So instead of a consumption of a 500 kilowatts, it's going to consume around 666. That means unnecessarily we are wasting that much amount of energy, right? And if in case if I'm increasing it to zero point 0.9, how much it is? Like 0.95, right? So that means like your 500 divided by 0.95. So it's going to be 526. It's just a 26 addition because nothing is like 100% efficient. We can't guarantee that one. If it is unity only, then the same is going to run for 500 kilowatt. But this is far better, more enough, right? Maybe far better, maybe minimum. I mean, by installing the capacitor banks, I'm going to increase the power factor. So the target is nothing but I have to increase it up to 0.95, right? From 0.75 to 0.95. So what I have to do, like first we have to calculate the initial reactive power with this load. Okay. What is the load? 500 kilowatts. And what is the power factor? 0.75. And what is the formula? It's Q initial is given by P into P is nothing but the active power that multiplied by tan of cos inverse the power factor initial. That is your 0.75. Okay. 0.75. So just with a scientific calculator, you can do this one, right? Or else just let me prepare an Excel sheet for this and I'll send you. Okay. So no need of any manual calculation. So cos inverse, there's nothing but cos inverse of 0.75. If you check it out in a scientific calculator, how much it would be? Is nothing but which is the angle for the current power factor. That's like around 41.41 degrees it would be. Okay. Cos inverse of 0.75. So why do we need this cos inverse? Because we are finding out the reactive power. Active power is cos theta. So it may be like a sine theta, it is reactive power, inverse of your power factor, right? That's your reactive power. So cos inverse of 0.75 would be 41.41. Okay. And then what we have to do along with this, the exact formula is like tan P into tan of 41.41, right? Tan of cos inverse this one. So tan of 41.41 would be like 0.87. That means 500 is the active power that multiplied by 0.87, right? 0.87 is like 435 kVAR. So I need a capacitor. How much? Like now the reactive power is like 435. Now I cannot decide upon what capacitor I require. Okay, just remember 435 kVAR. But how much power I'm losing? Like around 666 kilowatts it would be if I'm going to run this load with this power factor. Okay, that's going to be the problem. Now it's 435. And similarly, after this, after improving the power factor, the same formula we have to apply. I mean, only the power factor we have to change. I mean, like we have to change with 0.95 instead of 0.75 as we did in the previous step, right? The same cos inverse of 0.75, now it becomes 0.95. So how much it would be? The angle would be for cos inverse of 0.95 is 18.19 degrees. Okay, it's going to be 18.19 degrees. And then the final formula again, 500, that's nothing but P into tan of cos inverse 5. So 500 is the kilowatts that multiplied by tan of 18.19 degree. In that case, how much? It is 500 into 0.33. So this is just 165 kVAR minimum. Only just 165 reactive power. Why? Because like power factor is high, like 0.95. So how much we got? 165. And in the previous case, how much we got? Like 435, right? 435. And here we got 165. Now we have to find the difference. So that's the major formula. Like what is it? It's nothing but like in the previous slide as I showed you, right? Over here you can check Q required. The reactive power required would be equal to the initial minus the target. Okay. So initial would be always high. With a low power factor, the value would be high. How much it is? Like 435 kVAR it is, right? 435 kVAR it is. And with the target, I mean, after applying this 0.95 power factor, I'm getting just 165 only, right? I'm getting just 165 kVAR. So in this case, like just subtract it, okay? In order to determine the required reactive power compensation, Q initial minus Q target, 435 minus 165, sorry. That means 270 kVAR. So what is the capacitor bank size required? It is like 270 kVAR is required. And again, it depends. This 500 kilowatt in the sense, maybe many number of motors might be there or a single motor, whatever it is. Like just you can divide the capacitors as I showed you. Okay, in this case, it's nothing but like what you can do like with a circuit breaker, yeah, we have a contactor, then just install the capacitor over here, right? Like a 50 kVAR, okay? And similarly, once again, 50 kVAR, then again, like 50, okay? 50, 100, 150, and up to how much we need, like around 270 is required, right? So five 50 kVA capacitors, okay, like 1, 2, 3, 4, 5, each 50 kVA. This is also 50, this is also 50, this one also going to be a 50. So 50, 100, 150, 200, 250, and one 20 kVA, okay, 120 kVA we can install. So that means this would be how much stages? Like 1, 2, 3, 4, 5, 6. It's a 6 stage capacitor panel. And finally, along with this capacitor bank, what you have to install as per the transformer load. Don't check this value, just check the total transformer capacity, maybe 1000 kVA sometimes. Okay, might be, for example, if it is 1000 kVA, because this load itself is like 500 kilowatts. So at least minimum your size of your transformer would be something around 1000, right? 1000. So just 3% of this 1000, right? 3 by 100. So it's nothing but how much? Like a 30. So an additional 30 kVA. Okay, 30 kVAR. So this 30 kVAR would be your direct capacitor. Okay, this is a 6 stage. 1, 2, 3, 4, 5, 6, along with a DC or a direct capacitor of around 30 kVAR, right? So this is how you can design the capacitor banks, I mean, in the future. Okay. And other things would be like supplied by the vendor itself. There is a relay actually which is going to sense and automatically this is going to operate. How it is going to operate? Whenever a motor starts, okay, initially the starting current would be high so that the reactive power also is high. So that reactive power value would be read by from this APFC panel. That means there is a relay, sensing relay, along with the CTs, because direct current we cannot pass it to relays, right? Just 5 amperes relays it would be. So a current transformer is required, which is going to reduce the current like up to 5 amperes, and then it's going to sense that reading, and as per that reading, which is going to automatically switch on or switch off, like it's going to switch on the capacitors. Once the reactive power has been compensated, automatically it's going to switch off that particular capacitors also. Why? Because only during starting the current, I mean starting of the motors, the current would be high, and then it gets normal. Like when the motor reaches its full load speed, it's going to run in the normal condition, right? So at that point of time, the capacitor should be like automatically switched off. Earlier on, it was like manual handling. In that case, whenever we are starting any motor, we are going to switch on that capacitor directly. There is a selector switch now also. I mean, hand off and auto, right? That means for maintenance purpose, we are going to operate this in under manual condition. And in case of normal conditions, yes, it's going to work in automatic mode only, right? Normal conditions, it's going to work at automatic mode itself, and no issues with this one. Okay. So this is what the capacitor banks, maybe a few other types calculations also I'll send you apart from these things. Okay. Like few of my project details also I'll send you, because like I had to remove some project detail informations, and then it'll be sent to Augmentech actually. Okay. They would be sending you. So this is what the capacitor banks actually. Okay. So now we have some SLDs also. So just let me stop sharing this, cause I have scribbled over. Right. So we have some ELV systems, and then I'll show you a few AutoCAD drawings related to this ELV systems. Like, what do you mean by ELV systems? Nothing but extra low voltage works, right? So ELV in the sense extra low voltage. Okay, extra low voltage. Fine. So that's what we call it as an ELV. Okay, extra low voltage. Fine. So what are the systems we have? Like a PA, GA. What is it? Is nothing but the speaker, right? So we have a speaker system. Okay, fine, in your buildings. And apart from this, what are the other things? Like we have CCTV system. Okay. Then we have this access control system, like for your, with the help of biometric system or with your IDs, you're going to open the doors, right? Especially in case of official or commercial buildings, right? And any other systems like your data and voice. Okay, there's also an ELV system. So what is this data or voice? Like in your power layout itself, like we have the sockets, okay? Like we have the sockets. And after the sockets, yes, we have the voice and data points also. Voice means for telephone and data for internet, right? For telephone and internet, we have this voice and data points. So usually how the connections would be, like for the sockets, yes, it's from a DB. We are wiring it, okay, fine. But for this, for this data outlets, we call it as what? Like the data outlets. For this, we are going to use this Cat5 or Cat6 cables, okay? The category 5, category 6 cables, like all Ethernet cables, we say, okay? The data cables or Ethernet cables. So that would be connected from this outlet up to a panel called a patch panel, right? So there is a panel called patch panel. This is nothing but like in terms of electrical is a kind of a bus bar, like is a junction, okay, where we are connecting all these data outlets, okay? It's like kind of a junction. And from this patch panel, it will be connected to a switch or a router, okay, for the operations purpose, switch or a router, and then to a main server, okay, to a main server or to your data centers, etc. Main server. And for main server, where do we get the connections from? Like we from the main fiber optic cables. That means a telecommunications provider, right? Usually, like whoever is the telecom provider, they want to provide the network or the data, the internet connections, right? Internet connections with the help of fiber optic cables. Earlier on, we have been using that copper cables, but nowadays is like purely with fiber optic cables only. Okay, very light. I mean, the size also is light in size, and moreover, it's not heavier. And of course, it works. I mean, the data transmission speed would be very high, like at the speed of light. It travels with the speed of light actually. So the data transmission would be very high. Okay, the range. Similarly, in case of Cat 5 and Cat 6, like up to a certain range, your Cat 6 is like far better than Cat 5. The transmission capability would be high, the data transmission or the voice. Okay, but there is a certain ranges also like up to 100 meters, so etc. Fine. So that's your voice and data. So before that, maybe just I'll show you this PA system, like we call it as a speaker system, right? This speaker system usually we use for, nowadays we are using it for another purpose called voice evacuation. If in case if you might have studied in your firefighting system also, right? Like apart from fire alarm system, like we can use this kind of voice evacuation also. Voice evacuation in the sense the normal PAGA system, the normal speaker system. Uh, Along with that, whenever we use along a fire microphone, right? So we can connect it along with the fire alarm panel also. We can interconnect it, like with the help of interface units or relays, right? I hope you have done with your fire alarm also, right? In your firefighting system itself, you would have studied the fire alarm systems. Okay, fire alarm is nothing but just we have the detectors and a fire alarm panel detectors in the sense a fire smoke detector, a heat detector, and carbon monoxide detectors, etc. And for taller places like atriums or assembly areas, okay, we use the beam detectors. In case of duct, we use duct detectors. Okay, so and the notification devices we have like sounders, horn, buzzers, flashers, etc. Okay, so that one. Apart from that, like there is a thing called in case of your firefighting system. Maybe you would have studied this one. Like there is a thing called a phased evacuation system, right? Like a phase by phase. Like if in case for a multi-story building, if the fire occurs, might be like a 10-story building. If it occurs in sixth or seventh floor, for example, seventh floor. So this fire alarm system is going to give a general signal. That means, all over the building, it's going to get activated. So in that case, maybe all the occupants would be running here and there, and there would be a kind of a chaos actually. So in order to avoid that, what we used to do, like a phased evacuation would be far better. But that means like only the speakers would be activated in that particular floor, not in the, below or above the floors, right? Not below or above the floors, only in that particular floor. So that like the speaker, somebody in live or might be some recorded messages, okay, they would be exactly instructing only those occupants to move out of the building. Like that might be through a stairwell pressurization system or a fire exit, so that the system will be easy for evacuation system. That's what we call is like a phased evacuation system. For that purpose also we are using the speakers nowadays, right? Like a voice evacuation system, we say usually the same speaker system, but we are connecting it with fire system. We are interconnecting with the fire alarm system also. Okay, So then, like floor by floor, wherever the fire occurs, like through the sixth floor or it comes down to the fifth floor or whatever it is, phase by phase, we can evacuate the people. So at that point of time, the rest of the, I mean, microphones, that means the normal microphones, they are not going to work. Only our fire microphones is going to work. Okay, that's the setup actually, it would be fine. So apart from that, for normal purpose, we are using this public address system. For general, I mean, any birthday greetings or for playing music or whatever it is, we use the systems. Nothing but we have the speakers, woofers, subwoofers, or amplifiers, etc. That's it, right? The same concept is going to be. So this is nothing but we call it as a PA or a speaker system, passenger, not passenger, public address system. Okay, public address or general address, we say PA or GA system. There's nothing but an audio distribution system which is designed to amplify the sound so that it can heard over a wide area. So there are different types of speakers. We have ceiling mounted speakers, as you can see in this picture, or wall mounted speakers, also normal speakers also. Okay, it comes with different watts like 10 watts, 30 watts, 20 watts, etc. And a public address system or a PA system. There's nothing but a public address. So what are the components we use? Like microphones. I think you might be knowing this microphones. It's nothing but which is used to capture the voice or sound for a PA system, right? Microphones can be wired or wireless. There are two types, or handheld, lapel, or mounted also. Okay. And we have the mixer. What is this mixer is going to do? Which is going to combine multiple audio inputs from the microphones or any other musical instruments and so on, which is going to adjust the sound levels. You might be familiar, you might be using all these kinds of, like if you have a home theater at your home, etc. So there will be mixers also, so which allows for control over the sound quality and volume. For that purpose, we use this mixer. Like in a concert hall, okay, this is going to balance the audio inputs from a singer microphone, a guitar, and other instruments to deliver a balanced kind of a sound. For that purpose, we need this mixer. And then amplifiers. Amplify, what it's going to do, it's going to boost or it's going to increase the, I mean, it's going to strengthen the signal. That's what we call as an amplifier, right? It's kind of a switch which is going to strengthen the signals. That means it is going to boost the audio signal from the mixer so that it can be projected over a larger area. Now, in case of high-story buildings and multi-story buildings, we of course we need these amplifiers. Like in case of airport, that's the best example. Amplifiers ensures that announcements can be heard closely, like clearly across the terminals. And then the speakers, a very important point. Okay, this is what we are going to install. Usually, like in case if you consider an official building, maybe when we're installing in the corridor area itself, not might be in some cases might be inside the rooms, like few of the rooms we require, but maximum cases like in the corridors it would be, so that like different offices would be there and there is a single corridor, so the sound is audible. Yes, of course, all the persons are going to live outside the buildings, right? Okay, so might be maximum provided in case of this corridors, etc. I'll show you a sample drawing. So it's going to transmit the amplified sound to the audience. Okay, that's what it is. And for example, in a shopping mall, we have wall mounted speakers. They relay what announcements across the floors, open areas, etc. Similarly, in case of commercial buildings, maximum we'll be having this, ceiling mounted speakers, right? Maximum we have this ceiling mounted speakers. And we got this control console. What is it? Which is going to act as the main interface for the managing the system. That means which is going to control the area which is going to receive the sound, adjust the volume level, selecting inputs, etc. Like in a corporate office, what it's going to do, the PA operator to make announcements specific to different floors or departments, like a kind of a voice evacuation system, as I already mentioned, right? Similar to that. And zones and zoning controllers are also required. Usually, like this multi-story buildings or high-rise buildings, we have to divide it into zones, whatever the work it may be. I think you might have studied in your HVAC, firefighting, etc., right? Like for HVAC or for ducting purpose or for your firefighting, for sprinkler system or hose reel system. I think you would have studied the zones, different zones. We are just classifying into different zones actually. Okay, maybe fire alarm systems, like we need zones. Why? Because there are two types in fire alarm. One is like a conventional type of panel. The another one is going to be addressable type. If you're using conventional, that's for a smaller buildings, like maximum up to 30 detectors you can connect, right? 30 detectors. So that becomes one zone, one of the zone. The other zone would be next 30. Like zone 1, zone 2, zone 3, zone 4. It depends upon your building size. Maybe like if you have 6 stories, okay, zone 0 is like ground floor, then zone 1, zone 2, zone 3. Or else if it's a larger building, the same floor, it could be like divided into different zones, zone 1, zone 2, etc., right? Zone 3, zone 4, etc. So that's your zones actually. So depending upon the zone, we have to classify it. Okay. So zoning allows the operator to choose specific areas in order to send the announcements, music, or alerts, etc. Right. And the zone controllers, they manage audio distribution based on these areas actually. Okay. Like in hospital, this is the best example, right? Like we have separately address waiting areas. So usually you would have seen like in hospitals, whenever you visit an hospital, like they would be calling any like a doctor or a nurse or a ward boy, something like that, right? Usually if they require that person. So that'd be the regularly they would be doing some kind of announcements, right? And in airports, yeah, they want to do some announcements, etc. That you would have seen. Fine. Like staff areas, etc. Okay. So like maybe in the nurse care units, right, nearby the bedded units, it's required actually, mandatory, right? Okay. And the basic PA system, like what it consists, simple system like which consists of a microphone, amplifier, and speakers. Speakers along with woofers, subwoofers, etc. That we might be having it, right? Like in small venues like classroom, conference rooms, etc. Like in a retail store, a basic PA system enables staff to make announcements over a few ceiling speakers. You'll be able to get this one. Usually in shopping malls and all would be getting these announcements. And distributed PA system in the sense more complex it would be. Basic is like the retail shops or schools, classrooms, or that's it. But in case of distributed PA systems, little a complex system which would be distributed over a large area with multiple zones, different zones we have, and so hence we need the multiple speakers also, right? Often used in buildings with several floors or large open spaces. Yeah, usually in large open spaces we use, like for example, in university campus, distributed PA system, which is going to allow the announcements to be made in different buildings from a central control room, right? Like if you consider university building, that's going to be quite different. It may not be a high-rise building, but still, different buildings like this department separate, that department separate. Computer science or electrical or mechanical. We have different departments, HR and admin. So like we need these announcements, okay? That's like a kind of a complex system it is, right? It's not, it doesn't comes under the same story or the same flows. Okay. And we have a network PA system also. What do we mean by it? Like, which is going to use digital networking in order to connect the components of IP, like Internet Protocol. This is what that, as I told you, that addressable fire alarm panels, etc. Right? What it means, like each and every detector would be having an address. What is it? Nothing but the IP, Internet Protocol. Okay, Internet Protocol and addressable it is. So which allowing control over a network actually. So which is useful for large or multi-size organizations, a global corporate office. Okay, they can use this kind of networked PA system in order to make announcements in their regional offices or connect multiple branches also over this IP. That can also be done. Okay, so this is nothing but the technologies, like all embedded systems usually. And then we have this wireless PA also, not wired. So this is nothing but the only cons or the advantages, like we don't use wires in this case. Okay, but maybe like areas with challenging layouts, etc., we can use this wireless type, right? Like in an outdoor event or a fair, a wireless PA system allows flexibility in speaker placement. So this is a very great thing, right? Okay. So these are the major purposes. Like, why do we use these speakers? What is it like for emergency announcements and for the announcements in public spaces? Then for background music, yes, of course, like we're going to play the background music, and for event and any entertainment venues and educational institutions, of course, then paging and intercom services, etc. So whatever it is, like for each and everything, we have a thing called decibel level, right? The sound, the audible level. That should be maintained. Like might be like in case of fire alarm system, once you have installed all the sounders or flashes, what you used to do, we used to test the decibel level with the help of a decibel meter. Just carry the decibel meter at your hand, and just if you switch on it, just you're going to measure the sound. You're going to activate that particular sounder or the speaker, and just you're going to check the decibels, like with door close and door open, etc. Right? You'll be getting different decibel values, and that is a normal range that we have to maintain. If it is above that or below that, both are problem, both are issues, right? Above the decibel value, maybe it would be like irritating for the ears, and if it is below, also we may not be able to clearly hear that one. So there is a certain standard, as you can see, this as per the location. These are the set sound levels. Okay, as you're seeing it over here, as per the different location type. So these are going to be the average sound levels in dBA, in decibels. Like for business occupancies, like 55. Educational occupancy 45. Industrial, yes, it should be 80. Why it is 80? Because always like all the machineries would be working and it may not be that much audible for us, right? So we need a higher decibel level. And institution, 50 is enough. Mercantile, yeah, 40. Mechanical rooms, 85 is required because all the machines are going to work your AHU sound and all those things. And in case of water surrounded structures, 40. Place of assembly, it's 55. Residential occupancy is very less, like 35, right? Storage, 30 is enough. High density urban areas, 70. And in case of thoroughfares medium density, it should be 55. And thoroughfares rural and suburban, it should be like 40. Tower occupancy is 35. Then underground structures or windowless structures, 40. Finally, vehicles and vessels, it should be 50. So just you can just check out all these dB levels, and depending upon that, you can select a speaker. Okay, for what applications we are doing it, just we have to select the speakers actually. So there is a simple general calculation for your spacing, okay, like how much spacing is required from each speakers. So with this, like we can design like how many number of speakers also would be required, okay, in that particular area. So it all depends upon the room size for spacing, right? So room size, what we have to do is nothing but whatever the height it is, right? With respect to the height, we have to just multiply it with by 2, that's all. So for example, like for speaker height, push ceiling mounted speakers at least almost like 2.5 to 3 meters, or it depends upon your ceiling height, the fall ceiling height, right? At the fall ceiling height, we are going to install the speakers. Usually, normally it'd be 3 meters or 8 to 10 feet. Okay, so the distance between the speakers, it should be like height multiplied by 2. That means twice your height. That's it. That should be the distance. For example, if the ceiling height is 3 meters, then we should place the speakers approximately almost like 6 meters apart, or maybe less than 6, but it should not be greater than 6. That we have to ensure. Okay, maybe less than 6 also we can place it, not an issue, but it should not be more than 6 numbers. Okay, this is just a sample, like how to space this speakers normally, right? How to place this speakers. So just an example calculation you can see. For example, this is your total room. Okay, if your total room dimensions are like with respect to length, width, and height, 30 meters length, or 20 meters width, and 3 meters height, and ceiling speakers with a 90-degree coverage angle. Okay, not like complete 360, like a 90-degree coverage angle it is, and 10-watt power rating. Maybe 30 watts power rating is also available. Just a 10-watt power rating, we are selecting it. Okay, so what we have to do, like determine the ideal distance between the speakers. What should be the distance like with respect to the height? If it is 3 meters, 3 multiplied by 2, right? So the spacing should be how much? Like 6 meters, right? Like 6 meters it should be, like in order to, ensure the overlapping coverage also, right? The overlapping coverage also. So now we can calculate the number of speakers. How we can calculate? Along the length. Okay, it's a very simple calculation. Along the length, what is the length? Is like 30 meters, right? The length is like 30 meters. Okay, it's nothing but like just simple basic maths only. Like this is your total, I mean, sorry. Right. So if this is your room, okay, this is the total length, like 30 meters. And what is the width is like 20 meters. Okay. So keeping in mind like 6 meters should be the distance, right? Like 6 meters should be the spacing. Okay, because the height is like how much? 3 meters. So 3 multiplied by 2, 6 meters. So 6 meters in the sense for 30 meters, how many speakers we can install by maintaining 6 meter distance? Like almost like 5 speakers, right? Like 1, 2, 3, 4, 5 speakers we can install. Right. So this is with respect to the length. Okay. With respect to the length. Similarly, with respect to the width, how much it is? Like 20 meters, maybe 6 into 3, 18. Okay, fine. That's not an issue. Like 3 speakers. Okay. That could be like along with your width, like here and here, right? And here. So by this, we can calculate the number of speakers. So it's 5 into 3, like around 15 speakers we can install. Okay. Like 5 speakers spaced 6 meters apart, and these 3 speakers also, this also should be 6 meters apart. Okay, this distance also. So distance like the spacing from one speaker to another speaker horizontally should be 6 meters or less, and for the vertical distance also, the vertical spacing also should be 6 meters or less, right? Vertical spacing also should be 6 meters or less actually. So this is how like we can decide the number of speakers. Okay, just with the distance spacing, then we can calculate the total number of speakers required, right? We can calculate the total number of speakers required. Okay, that's what simple thing. Okay, it's a more basic thing actually, and I'll show you the drawings also. Okay, so there's a thing called inverse square law for sound dispersion. Okay, this we have to uh, take care on this point also, right? Maybe I'll tell you clearly what it is. The inverse square law in the sense, which is for a sound dispersion, explains like how sound intensity decreases as it spreads out from a source, right? Everything, each and everything has got a coverage range. After that, yes, it is not going to be effective. So that means according to this law, the sound intensity that would be normally measured in decibels, dB, right? So which decreases by 6 decibel each time the distance from the source doubles, right? The distance from the source is going to double actually. So there is a formula for this inverse square law. The SPL new. What is this SPL? Sound pressure level. Okay, sound pressure level that would be equal to SPL, the reference, the first one. Okay, in an example calculation, you will understand that one. The sound pressure level for the first or the reference one minus 20 into log 10 of distance new by distance reference. Okay, so SPL new is nothing but we call it as the sound pressure level at the new distance. SPL reference is nothing but the sound pressure level at the reference distance. Distance new is the distance at which we want to calculate the sound pressure level or the SPL, and distance reference is the reference distance. Often 1 meter from the source it would be, right? Often 1 meter from the source it would be. So just a calculation. Now you'll clearly understand it. Like as the, I mean, what it is, what it means is like the distance is going to matter. Okay, if the distance increases, what happens? Your sound level is also gonna decrease. Okay, maybe I'll show an example. Like suppose there is a speaker which produces a sound level of 90 decibels, okay, at a distance of 1 meter. Let's calculate the sound level at distance of 2, 4, and 8. This would be provided by the manufacturer itself, right? They have a certain range, how much it can cover, like 90 decibels. It could be up to 1 meter. After that, is definitely is going to decrease. So what would be at 2 meters? So first, what we have to do, we have to find the reference SPL. What is the reference SPL? 90 dB at 1 meter, right? 90 decibels at 1 meter. Okay. And what is the new distance? Like 2 meters. So the formula, as we know, like it's nothing but the SPL reference, right? So that 90 dB minus 20 into log 10 of what it is, like the new distance by the old distance. That is 2 by 1. Okay. Or else you can just check the formula over here, right? This is the formula. SPL new is given by SPL reference, the existing one, minus 20 into log 10 of the new distance, like the increased distance by the old distance, whatever it is, the coverage range, right? The distance reference. So that would be it's 90 decibel, 90 is the reference, minus 20 log 10 of 2 is the new distance, by 1 is the old distance. So 90 dB minus 20 into 0.3 log 10 of 2 by 1, it would be like an online calculator. I mean, the scientific calculator will be able to get this one, 0.3010. So that would be around 90 dB minus 6 dB is 84 dB. So what happened now? Like at 1 meter distance, the sound level was around 90 decibels. But when I'm increasing it to 2 meters, in that case, what happens? The decibel level decreased from 90 to 84, right? From 90 to now it's like 84 dB. Similarly, if I'm doing it for 4 meters, right? For 4 meters with the same formula. In that case, what happens? Like you can see this. In case of 4 meters, the same formula, 90 dB, the reference SPL, minus 20 into log 10 of the new distance. Now, 4 meters, what was the old one? The existing one for 90, it's 1, right? So 20 to 0.6021, it'll be like 12. So 90 minus 12 dB, it's 78 dB. Further, the noise level decreased, right? Further, the noise level got decreased. So this is the basics actually. So this is the way. Okay, this is the way like we have to decide upon this speakers depending upon the distance. Fine. And now finally, if there is any outdoor speaker placements, okay, if there is any outdoor speaker placement, so that means for outdoor PA systems, what we have to consider, like the factors like wind, all the other external factors also has to be considered, right? All the other external factors is also to be considered, like wind, the background noise, and the need for increased SPL also to cover a larger distances, right? And spacing for large open spaces like assembly areas, workshops, etc. In that case, speaker spacing generally ranges from 10 to 15 meters it is, depending upon the amplifier power and the speaker coverage angle. So if you have a good amplifier, then it's well and good, no issues, right? If you have a good amplifier, it's well and good, no issues. And maybe I'll show you this drawing actually. Like this is a PAGA layout, okay? So how the connections would be like this, we are connecting it to a fire alarm control panel as I'm showing you, right? This we are connecting it to a fire alarm control panel because in case of fire, we can use the same system for voice evacuation also, right? Not just for general announcement, we can use it for as a voice evacuation system too, right? So here it is a 6 zone audio main controller we have. That depends upon the different number of zones actually. So we are connecting it to amplifiers with different watts, right? Many number of amplifiers would be there, and we are connecting it to a DVD player in order to play the music and other things, right? And we're connecting it to the microphones. That's what more important, right? FAP and PS interface unit is also required. So these are the symbols for your speakers. It's nothing but like what it means. It means 6 watt speaker it is. This is a horn type speaker. This is a box type speaker. This is an amplifier. Well, it's mentioned over there itself. VC means a volume control and a microphone. This is more important. Then a VCD player to play music also. And this is your flexible cables, okay, like the data cables. I mean, for your public announcement system and a main controller, right? Like a main controller is required. Okay. So just a sample layout I'll show you. Okay. Like just consider in each and every floor. This is just the riser drawing. What we mean by this one? This is just a schematic or a riser drawing we can say. So as per this, that the hotel building that you have worked for this HVAC and other applications, right? The same building. So if in case if you want to install this PA system, right? This passenger, I mean this public announcement system. In that case, where it is required, yes, of course, it may be required in each and every floor, in all the floors. That's what is shown over here also, right? Almost up to your roof. I mean up to your eighth floor. Okay, we have a basement, right? A ground floors, a first, second, third, and like up to I mean eighth floor we have. But right from second to eighth, it's like typical, right? It's like typical. So the same number of speakers it would be, right? The same number of speakers we have. Fine, like up from right from the second floor. Okay, right from second floor up to eighth floor, it's going to be the same number of speakers. Okay, that's fine. Then what about this floor and I mean the ground floor and first floor? Like we have some other concert halls also, right? Like ballrooms and other things. So might be little more number of speakers would be required, right? Little more number of speakers would be required. So the best example I'll show you, like this is a typical, okay, from second to eighth floor. So we have a single speakers, like we have different rooms, individual bedrooms over here, kind of a hotel, right? So we have the bedrooms. So in all these bedrooms, we are providing one speaker over here, like one each individual speakers over here. And in case of corridors, it depends upon the distance, right? So what you have to do, so just check the spacing over here as we discussed already, right? Just you can check the spacing like from center to center, right? Like center to this center, you can check it out. So it's like almost like around 7.076. Okay. So what is the area actually? It's like 2.7 meters. So it's better. Okay. In this case, what I mean to say is like if it is better, if it is like 2.7 meters, right? Height is 2.7 meters. This is the false ceiling height. Okay. 2.7 meters. So 2.7 multiplied by 2, how much it is? It's going to be like 5.4, right? If I'm right, it's 5.4 meters, right? So with a distance of 5.4 meters, you can install the speakers rather than like with this 7.76 meters. So this is like 7076 That means it's exceeding, right? It's exceeding. So better you can place it with 5.4 meters. That means maybe another one or two speakers you can add to this particular corridor area. This is just done as a sample, right? Just done as a sample. So just you can add one or two speakers over here, right? You can add one or two speakers in order to compensate that one, the distance actually, okay, based upon that. And here we don't need any calculation because for each and every individual bedrooms, we have decided, yes, of course, I need one speaker. That would be fine. Not an issue. The height is like 2.7 meters. And anyway, no need of distance at all. If you calculate distance also, it's going to be less. Okay, like height is 3.5 meters and total height, and false ceiling height is 2.7. And here it is the carpet area, like a corridor area, like around 150 square meters, and maybe either another additional one or two speakers you can install. Okay, that you can do it, or else it depends. It depends upon your client actually, whatever he prefers or he requires, right? Maybe in case of official buildings or industrial buildings, we have to definitely follow the standards. Like for example, here in first floor, as I told you, we have this festival halls or the concert halls, right? Like the ballrooms where some functions, some dance programs, whatever it is, would be conducted. And here we have an AHU room. In case of EHU room, we used a different type of speaker, as you can see this, right? So what is that particular speaker? Like that BSP, as you can see, is nothing but a box type speaker we have. It's cause no ceiling, right? we don't have any ceiling in case of your AHU rooms. It's a mechanical room. So just a wall mounted speaker we are using, it kind of a box mounted speaker. But the rest of the rooms, yes, there is a false ceiling. It clearly shows you like there is a false ceiling, right? So we used to install it in the false ceiling itself, right? So the normal speakers, your normal speaker, how many speaker we consider? Like four number of speakers. Like as we did the calculation, as I showed you the calculation, similar to that. So what is the height? It's 3.5 meters, right? 3.5 meter is the height. Okay, and with respect to the length and the width of the room, you can decide upon the number of speakers. So just cross check whether the distance is like 3.5 in the sense. It should be at least maybe up to 7 meter distance. It could be, right? And here we have exactly 7 meters as you're seeing it over, right? So the distance with the spacing between the two speakers is like 7 meters. How we decide upon it with respect to this height, okay, the false ceiling, because we are installing the speaker in the false ceiling only, right? We are installing at the false ceiling only. So 3.5 multiplied by 2, it's 7. So similarly over here also it's 7. And just check the distance from with respect to the width also, width or the length also, right? So again, you can cross check this one. So this distance, right? This distance is like 6.3. Yeah, well, under less than 7. So not an issue, right? So like minimum we have decided that like four number of speakers would be required, right? Like four number of speakers would be required in this particular room, right? In this particular room. Okay, this is not that critical actually. No, just or else like in consultation with the client, okay, wherever they require the speakers. But this since a ballroom, I mean the festival halls, etc., the dining area, yes, of course, we need the speakers in this case. Like similarly, like as you can see, this everything is connected in a loop, and we are connecting it to the controller. That's it. Finally, right? We are connecting it to the controller. Okay. So, in case of this dining area, yeah, of course, with respect to the spacing that we have to decide, both horizontal and vertical, right? So again, you can check the dimensions, not an issue. Just you can check the dimensions, right? So it's nothing but how much it is, like 6.9, yeah, under 7 meters, right? Like under 7 meters. And here also, and with the speaker, you can check. It's like how much? Like 6.236. Okay, 6.236. Fine. So it's well, everything is under control. I mean, as per the calculation, no issues. Either it should be like false ceiling height is 3.5 meters. That means the minimum distance should be 7 meters. It should not be 7 meters and above. That's what the main concept is, right? It should not be 7 meters and above. Okay, maybe it may be less than 7 meters. That's not an issue, but not above 7 meters actually. Similarly, over here also. Okay, the same concept. Like wherever the area it is required, we have to decide. I mean, install these speakers, right? Here it is 3.5 meters, so maybe 7 meter distance we can fix it up, right? In this building, and this building is also going to be the same. It's more or less your ground floor and first floor is same with the festival halls, and we got this ballroom, right? Festival halls and ballrooms, etc. Might be there, might be an office room, yeah, a conference room and an office room in case of your ground floor, right? We have an office room and a conference also, but it's okay, like more or less typical type. So just we are designing with respect to the distance and horizontal and vertical that you have to design. But in this case, it's small rooms over here. Okay, with respect to the length or the width, maybe only one speaker is enough, which is going to cover the entire. But the height you have to confirm, like it is 2.7 meters, right? That means 5.4. This is fine for each individual bedrooms. Like one speaker is enough. And in case of corridor, as I told you, the height is almost like false ceiling height. It's considered to be 2.7 meters, right? 2.7 meters. That means in the false ceiling only we are going to install these speakers, right? At the false ceiling we are going to install these speakers. So just ensure that it should be like a 5.4 meters distance. Okay. So in that case, what you can do, slightly you can include one or two speakers also, right? Just you can include one or two speakers. Like you can just adjust this one, right? You can adjust a little bit over here and there, and maybe another one speaker you can install. Might be like if you check the first distance from this speaker to this speaker, right? What is it exactly now? We'll check. Like just from center to center, I'm checking it. So it's like 7 now. Okay, they're maintained as 7, but actually how much it should be? Like 5.4 it should be, right? 5.4 it should be. So what you can do is like just you can bring the speaker. Okay, like maybe I'll just copy this. Sorry, I copied the line actually. The speaker I should copy, right? And maybe over here somewhere I'll place this one. Okay, just a sample I'll show you. Somewhere over here I'll place it. Right. And Then let's check the distance, right? Is like 4.8. This is under control. Or else what you can do, there's a simple thing, nothing much, just you can check the total length, right? So just you can check the total length of this carpet or the corridor area. How much it is like around 39 meters, around 40 meters, okay, 40 meters. But how much spacing has to be considered? Like 5.4 meters, right? 5.4 meters. So it's nothing but your 40 by 5.4. That's it, right? So it's going to be 40 divided by 5 point. Okay, it's 40 divided by 5.4. It's going to be 7.4. So at least 7. Okay, at least how much? Like at least 7 numbers of speakers are required. So here it is like 1, 2, 3, 1, 2, 3, 4, 5 only. So we need another 2 speakers. That's all. Okay, we need another 2 speakers. So what I can do is like just I am connecting it with this one. Okay. So with 5.4 meter distance, I can design it, right? With 5.4 meters, or this is fine, not an issue. Just I can move it further. Okay, maybe this I'll just move it a little bit. Okay, so just I can move this one. Right, maybe it's not required that exact distance I have to maintain, but it should be under or maximum 5.4. Okay, that's what it should be. Maximum should be like 5.4. That I have to ensure. Okay, this is too close. So just you can move this one. Right, somewhere over here, right? And here, this one also, let me move it over here. And one more, like how much we have? Like 1, 2, 3, 4, 5. Yeah, we have 5 only, right? 1, 2, 3, 4, 5, and 6 and 7 is required. So slightly I can move this one here. And you can move it like this. Sorry, maybe like at center. Okay. And this one, let's move it. Right. So 1, 2, 3, 4, 5, another 2 speakers. Okay. Just you can copy and you can paste it. Right. So exactly you can do it just as a sample I'm showing you now. Like it's like almost 7 speakers, right? As per the requirement. So now you can maintain that space also like that 5.4 will be available or less than 5.4, right? That's what is required for us. So how much it is? It's like 4.8 meters. Fine. And this one, like you can see, it's like around 5.2 meters. Well, under 5.4, and it's not such that equally we have to maintain because it depends upon the other services also are there, right? That also we have to consider. This is 6.1. So slightly there is a problem, right? So this what you have to do, you have to slightly adjust this one. Okay, maybe up to this area, right? And now you can check the distance. Yeah, this is fine. You can move it over here. And this one also, let me move it. And if possible, if in case, if another speaker is required, okay, well and good, you can install another speaker also, not an issue. Like 8, you can make it. You can round it up to 8 speakers also, not an issue. So just you can check the distance, right? Yeah, it's 5.05. That means under 5.4 meters. And here too we can check. This is also fine. Like we have 5.3 meters over here, right? So this is how we can do it. And just you can just draw the lines and you can connect it. That's not an issue, right? Like just maybe I'll copy the same layer, right? You can copy the, okay, you can do that one. Like maybe just you have to, with the help of the lines, you can connect it. That's all. Like you can use multi-line, right? Like polyline you can use, sorry. So like let me switch off this ortho. And you can use the polyline and you can connect it right with the center. And then we can change the layer also, right? Like I'm connecting it to this particular speaker, then uh, to this speaker at the center. And okay, these are nothing but just the connections I'm showing you. That's it. Okay. Simple with lines, you would be able to connect these things, right? Like this, like this, like this, like this, like this, and okay. Maybe one more speaker you can connect as I'm showing you. All right. So here you can just change all these things. Okay. Just select all these things and you can change the color, whatever you like. Okay. That's just a sample I'm showing you. So it's nothing but just in the properties. Right. So you can right click and in the properties, you can check it out like block. I mean, the color you can provide and layer also like line weight. If you want to change, you can change this, right? And maybe line type you can change if you want. Okay. So that's it all depends. Okay. Just the connections we are showing. That's it. Like a continuous line and maybe the line type scale. Okay. Let it be by layer. Okay. Let it be by layer. Fine. That's it. No issues. Okay, if you want to increase the thickness also you can increase. This is just showing you the connections. Okay, just showing you the connections. And here like instead of 1, 2, 3, 4, 5 speakers, yes, of course another 2 speakers you can add it. That's all. This is a riser drawing. Okay, just a riser drawing. Maybe right from your eighth floor up to the second floor, instead of using 5 speakers as per the height or as per the standard, you can use up to 7 speakers. Okay, just a sample it has been shown. You can use up to 7 speakers. So just include 2 more numbers. Okay, just include 2 more numbers. That's it. Like, and just name it also. Okay, maybe here. Okay, like, but the thing is like we have connected together. Just okay, just maybe 2 more speakers you can connect it over here, and just change the numbers. Okay, like 1, 2, 3, 4, 5. Right? Just change it to 1, 2, 3, 4, 5, etc. So totally like finally it'd be like 7 speakers. Okay, as I told you, as per the calculation, it'll be like 7 speakers in almost from second floor to eighth floor. So 2, 3, 4, 5, 6, 7, 8. So for 7 stories, 7 multiplied by 7, so like 49 speakers it would be. And in case of, I mean, in case of your first floor and ground floor, it's like almost 1, 2, 3, 4, 5, 6, 7. 7 in the sense, like including that AHU rooms also, right? Which includes another two types of. So totally it's like, again, 14 it is, again 14 it is. So like 14 plus 14, yeah, I mean, 49 till this one, 49 speakers, and we have 49 plus 7, right? 49 plus 7, how much we get? 56 plus 7, okay, like around 63 speakers, okay, whatever it is. So that we are connecting it to a 6 zone, like we have divided into different zones, right? As this is what the zone it is. Like zone 1, okay, zone 1 has been connected to this particular ground floor, and your zone 2 you can see this, which is connected to your first floor, right? First floor. And the zone 3, 4, and 5, okay, that's for respective the other floors. Okay, like these I mean your second to eighth floor, we have divided into different zones actually, right? Different zones. That means the topmost 2 floors comes under one zone, and the bottom zones will be like, you can divide it actually. Okay, like common zones, like this is a common zone, 1, 2, 3. Okay, like 3 zones we have, plus these two are separate, like fourth and fifth. Why? Because here there is a requirement, mandatory requirement for the speakers, because we have that festival halls, etc. So that's why like little more number of speakers are there. Okay, so like this you can divide into each zones and you can connect it to a zone controller. There would be terminal blocks would be available, and which is again connected to a DVD player. And then we have the amplifiers, then which is like with the help of an interface unit. Okay, directly we cannot connect it to a control unit. Interface unit is nothing but like a kind of a relays we use, right? We use the relays, and from with the help of the relays we are connecting it to a file alarm control panel, right? We are connecting it to a file alarm control panel. And then now we'll have a look on the CCTV layout and some CCTV components I'll show you. We'll have just a 5 minutes break and we'll discuss, right, Mr. Tony, Mr. Morosi? Okay, we'll have some 5 minutes break and we'll discuss that CCTV. Fine. Okay, right. Yeah, hi. Welcome back. Um, just we'll deal with this CCTV system also. So let me show you what is that CCTV general components. Okay. So might be you might be using at your homes also, or in different office areas. You might be able to find this CCTVs, right? So what are the main elements of a CCTV? Closed circuit television network, right? We have a camera, then we have a video matrix, a digital video recorder, or an NVR. NVR in the sense a network video recorder. Sorry. There are two types. One is a digital video recorder, and another one is a network video recorder. So, what is the difference between this DVR and NVR? Is nothing but if in case it's a DVR, everything like the image processing would be done by this DVR itself. And if I'm using an NVR, in that case, that's like an IP control, like what we say, like IP in the sense Internet Protocol system, so that the camera itself would be processing the image. Okay, in that case. So that's the advanced system, like connected to Internet Protocol. So that we have to use NVR, and this is a DVR, quite old model. Like nowadays, we use NVR, like network video recorder. Then a monitor, laptop, television, whatever it may be, and a control keypad, and the usual wiring system. What are the wiring required? Like a power wiring is also required, and of course, data wiring is also required. Usually, if it is of a DVR type, we need that coaxial cables. Okay, coaxial cables, which would be of copper inside that coaxial cable. And if in case it's NVR system, IP enabled, Internet Protocol enabled, in that case, it would be Ethernet cables like Cat5, Cat6 we can use. Okay, along with the power cables. Power in the sense here, what is the power required? Why do we call this one as a ELV system? Because is extra low voltage, just a 12 volt, a 24 volt, 12 volt system is required. So how we are going to get that one? Like we have a transformer, like usually the voltage would be how much? Like 230 volt supply, right? So we have 230 volt supply. So that 230 would be stepped down to 24 volt. Okay. And for the to 12 volt, right? 12 volt. And we have an SMPS, a switch mode power supplies. Like we got the rectifiers, the diodes, which is going to convert that AC to DC. So here the final voltage required is like 12 volt DC. That's what is required. Might be any other systems also, like it might be an access control system for access control panels, or for this door controls, etc. Like where we use these electronic sensors, etc. So for each and everything, we need a 12 volt DC supply. That's it. Okay. From AC, it should be converted to DC. So we need an SMPS actually, right? Okay. So both power wiring and like for all the cameras also, we need the power cable as well as the data, and for the DVR or NVR. So this is what, like, as you can see this, right? We have a, yeah, first we'll look into the cameras. These are like different types of cameras we have. Apart from this, also many number of cameras might be having, like a pan, tilt, zoom type, fixed camera, then a motorizing camera, then a day and night cameras, etc. And this is a DVR and this is an NVR. NVR and DVR in the sense, the image, whatever it is, the entire process would be done by this controller, this DVR, this, I mean, digital video recorder, we call it as. And cameras, nothing, it's not like analog cameras we use. It's not digital, like the analog cameras, normal analog cameras we use. And we have different channel inputs like 4 zone, 8 zone, like multi-zone inputs are available, right? And in case of NVR, it's like this camera itself, because it's a digitized like IP control. So they are going to, camera itself is going to process the image, and then it's going to send it towards this NVR actually. Okay. So that's the difference between DVR and NVR. As you can see, this NVR in the sense, it's recorder which is attached to a network, and it's going to include a software program in order to facilitate, right? So generally, it would be with an internet protocol, an IP address with IP. Okay, IP cameras rather than the traditional analog ones that we use in case of DVRs, right? That we use in case of DVRs. Since they work with IP cameras, NVRs use wireless technologies also. Either, there are two types. Again, if I'm using an NVR, either it could be a Ethernet cable like Cat5, Cat6 cables, I mean data cables, or else could be Wi-Fi also, like a wireless also, right? So they often also feature Ethernet ports also, either Wi-Fi type or with this Cat5 or Cat6 cables, right? Cat6 cables. And that would be connected with the help of RJ45 plugs, right? RJ45 plugs towards the controller or the recorder we have to connect it. So this is used with IP cameras. Similarly, if it is, I mean, the digital video recorder, so this is going to work with analog cameras only, right? That means, the cameras are not going to process the image and all. Only this digital video recorder or this controller is going to do the entire process, right? Entire process. So here it may be like, might be using the coaxial cables. That means for AV, audio video, like normal televisions you have at your home, right? For the cable TV connections, etc., would be using that old coaxial cables. The same type it is, right? So the DVR recorders, they process the uncompressed videos, the videos not compressed by the cameras, with a coaxial cables. From camera up to this DVR, the connection would be via coaxial cable, right? And then it's going to compress the videos to digital signal before sending them out towards your monitor or towards your display, right? So it works with analog cameras. That's what your DVR is about. Nowadays, like I think almost everywhere we have replaced it with NVR system, network video recorder. But in few cases, like in the old buildings, etc., not be using the same DVR itself, right? So these are the difference. Like DVR in the sense, digital video record is an analog type, right? That means to a traditional CCTV system, closed circuit television system, we can say, and NVR in the sense which works with internet protocol, right, via the internet. And here this is compulsory, it's mandatory, it would be wired only, right? But here it is wireless or wired. Wired in the sense here we use coaxial cables for data transmission is through coaxial cable, but here it could be a wireless. If in case it is wired, yes, no need of this coaxial cables, it's very hard, right? We can use just a Wi-Fi normal Cat5 or Cat6 cables, okay, in this case, why Ethernet cables we say. So here like multiple channels, like 8 plus cameras we can connect to a single DVR. Here also we can connect around 8 plus cameras, okay. Multiple channels are available in both the cases, like we have multiple channels, multiple cameras we can connect to a single DVR. If in case if it exceeds, then might be we need another DVR, okay. That depends on the size of the building. And here the raw footage would be processed and encoded by the DVR alone, by this digital video recorder or by this controller only. But in case of NVR system, the footage would be compressed, processed and encoded by the camera itself. Okay, you have to understand this one, which is encoded by the camera itself, right? And this is what the connections, as you can see this, which shows you just the backside, the terminal ports of your DVR, right? Or DVR or an NVR we can say, because we have different types of cameras, right? Different types of cameras we have, and we need power cable. As you can see, this 120 or 220 volt power supply. I mean the normal AC power supply. But what is the output? Output, as you can see it over here, it's like 12 volt DC, right? So here is the input, right? The input would be just a 230 volt AC, but the output would be 12 volt DC, right? It's 12 volt DC. Okay. So with the help of this adapter, like what we use for normally for our laptops, chargers, mobile phones, etc., right? Similar to that, SMPs we can say. And then power wiring is required for cameras also, right? For camera, we need both power and as well as data. Okay. Similarly, to this controller also, again you can see this to this DVR or NVR. This is a DVR, right? Oh, NVR. Okay, because we have the router also which works with internet protocol. Fine. So it's a kind of an NVR. So for this NVR network video recorder, a router is available. All the ports is available, like with HDMI that we are connecting with HDMI cable. We are connecting it to a laptop, a TV, or a monitor with help of VGA cables, etc. And these are RJ45 connectors. We are connecting it, and we have a USB port also. And for power supply, this also requires a power supply, and your cameras also requires power supply. So power wiring is also required. But what should be the power? With the help of an adapter. An SMPS, okay. It should be like 12 volt DC, it should be, right? 12 volt DC. We have to connect I mean, the power also is required. And the data cables, like in this case, it may be a Cat5 or Cat6 cable. It might be wireless also. Sensors would be available, or else should be a Cat5 or a Cat6. If it is DVR, the same. If it is like a DVR, in that case, what we have to do, like the cables that we are connecting it to DVR, this is a DVR. If in case DVR 1 to 16 channels are available, multiple channels, so the cable should be a coaxial cable. That means it cannot be a Cat5 or a Cat6 cable. It should be a coaxial cable, like the normal the TV cables that we use at our home, etc. Right? With a copper at the center, we'll be finding one common conductor, right? Be insulated, like it'll be like very hot also. But Cat5, Cat6 are very just simple wires. It is, I mean, very easy to terminate and etc. Okay, terminate the cables. So this is a general, okay, just a general idea. Maybe this document I'll be sending it to you. So in further in future, if you want to connect any CCTV system or speaker system at your home, like CCTV, if in case if you require, maybe just for outside, for just to monitor any intruder, etc. So you can just follow the same drawings, okay? Like multiple cameras you can install, but I don't think we are going to install so many cameras. Might be a few important places like in the outside, the gate areas, etc. So a 4 channel or 8 channel that would do rather than 16 channels also. It all depends. It all depends, and then you can connect it. But power wiring is required for both this DVR as well as your cameras too. This is like an analog camera. The same thing, if it is of an NVR type, then it's going to be a digital camera. Okay, so the camera itself is going to process the image and then it's going to send the message towards your, I mean, the information with the help of Cat5, Cat6 cable. That's like your voice and data, right? And usually the first and foremost AV cable for audio and video, yeah, we are using that coaxial, and nowadays it's going to be your Cat5, Cat6 cables for data and voice, what we are using it, right? Same, that's going to be. So, this is just the connections, and we can connect it to microphone, and other ports are also available as you're seeing it over here to the speakers, right? So all different ports are also available. You can just connect the cables, and this is the difference, the DVR and NVR. Okay, DVR you can see, right? Like we have a router, USB, HDMI out input, like 16 channel is also available, right? With respect to 16 channels are available, but here in case of NVR, you can see like 8 ports are available maximum, right? Like 8 ports. Maybe extendable version 16 ports would be available, but this is a normal, a general DVR, the old analog type, and this is the digital, I mean, with IP addressable type, IP Internet Protocol. That's your NVR actually. So the same terminals we have, just small changes. It would be there. A power supply is required. Here also power supply. Here also there's a router. Here also there's a router with a LAN connection, as you can see this, but different channels like 1, 2, 3, 4, 5, 6, 7, 8. Here's like 16 channel video input is available, but the cables that we connect from the cameras. So for this DVR, it should be a coaxial cable. Okay, only it works with the coaxial cables. But in case of this NVR, it could be a normal Cat5 or Cat6 cables that we can connect to this DVR, or else if sensor is available, fine. Then it could be a wireless connection also. Okay, it could be a wireless connection also, along with the USB ports, HDMI cables, as usual. If it is a VGA, as you know, the VGA port would be connected to a monitor, an LCD, or a laptop. And if it is like an HDMI, yes, we are connecting it to a television, right? A TV monitor. And router, okay, which is required, but here is where it's going to work an important part, like it's depending upon internet protocol, right? In case of your DVR, I'm sorry, NVR. And DVR, just unlock it as okay, unlock, but this is going to process the image. This DVR is gonna process the image, but here the camera itself is going to process and just send the information through this controller, and through this controller it would be sent to your I mean other thing. So yeah, and that option is also available, but still, Mr. Tori, like might a minimum power supply is required because Ethernet cables, they're not directly supplying the power actually. It's completely kind of a data or voice only. Okay, so the Ethernet cables, like nowadays, like special type of cameras are also available, like with batteries and other things. But still, like whenever we procure the battery, we have to confirm what is the power supply required. But as usual, like both power supplies would be required for your cameras and as well as your, I mean, for this, I mean, for this controller also. Okay, the basic power supply is generally is required for your DVR, but maybe nowadays the cameras that we get, maybe it's not that required as you're saying also. Okay, maybe we can check it up, like not an issue with different manufacturers. So here, this is the normal thing for camera also. Like as you can see, a video connection, a power connection, a small power connection is required actually. Okay, like a power connection is required. Like a battery pod cameras are also available. Just you can check it out in the market. But as usual, the basic concept is like the power supply is required for both your, I mean, the recorders and as well as the cameras too, right? The recorders and as well as cameras too, right? If I have any other different type, maybe I'll include it and I'll send it to you while sending the notes. Fine, Mr. Tony. Okay. I'll send it to you like in the notes. So this is a general thing. This is just a power drawing, which shows nothing, no data over here. So which shows just you the power layout, I mean the power wiring connections only towards your cameras actually, right? Towards your cameras, right? So now there is a layout for CCTV layout. CCTV is nothing but this is like as per the requirement we have to install the CCTVs, right? So we have different types. Like these are nothing but the different symbols as you're seeing it over here. Like varifocal dome camera. That's nothing but like which can have different focal lengths. You know, different. You can change that focal length also. Like in this case of this kind of a varifocal dome camera, we say. Then we have fixed dome type camera, right? Then a network video recorder. Here we are using an NVR, right? Here we use an NVR actually, as you are seeing it over here, and a CCTV monitor, a bullet camera. Then this is your Cat6 cable. Okay, so here there is no coaxial cable. Why? Because I'm using an NVR, as you can see this. The same, if it is of analog type, in that case, what happens? It would be a DVR, and then I have to use, coaxial cable. But now it's completely Ethernet cable, like Cat6 cable. Cat6 is a better version, higher version of your Cat5, so we can use this Cat6. And then we have this fiber optic cables. Okay, that's your main for the main connections towards your switches, like in core switch, right? And we have a PoE switches also. So that's nothing but this is a format, like as you can see, this is an 8-port PoE switch. The power, okay, we are supplying the power over here, then a core switch, and then all with Cat6 cables. Like we have a 32 channel NVRs in this case. Okay, it all depends as per your building size. The minimum is like from 4, 8 channel, 16 channel, 32 channel, etc. So from the core switches, okay, we are connecting it to these NVRs actually, right? NVRs actually. And again, with data cables, okay, we are connecting it to these monitors and computers, laptops, LCD monitor, television, or whatever it is, okay? Just a general data drawing has been shown, okay? Just a general data drawing it has been shown. And this is how the CCTV it is. And as I showed you the wiring connection. So here it is nothing but just for this ground level floor, we have the external cameras, right? Like this is nothing but, especially we use a bullet camera, right? In the external areas. As you can see, this one over here and one over here. This would be like we have to fix it up, like for monitoring purpose, right? Not, it may not be required in all the areas. No specific calculation for this CCTV system or no specific design. You can decide it actually, like based upon the building layout, like wherever you require, like in all the nook and corners, you can install. That's not a problem. So this is like the backside. We got the stairs. So this is going to be like an entrance. Yes, of course. We have a camera over here, right? And a camera over here. Okay. And this is like the main fiber optic cable, right? This is the main fiber optic cable, which is feeding the 8-port PoE switch actually, right? Which is going to feed this 8-port switch over here. And then from this switch, yes, we are connecting it, right? To different CCTVs. As you can see this here, there is a CCTV. What is this type? There's nothing but like a fixed dome cameras, right? We have a fixed dome camera over here. This is nothing but that at corporate area, like a kind of a corridor it is, right? A corridor it is. And here one camera we have at this angle and this angle. Maybe whoever enters or moves on, we need those details and all, right? Like here it is mandatory. There's like in a kind of an entrance area. And then we have special cameras inside this dining area, right? There is nothing but like a normal varifocal kind of a dome camera we have. Okay, we have the dome cameras over here, like we have installed one over here. Maybe one is enough. And here in this area, office area, we have one. And in case of conference room also, we got one varifocal camera, a dome camera it is, right? And yeah, and similarly in the topmost floors, like in the first floor, right? This is the corridor, right? Here we read, right? Here we need the cameras. Like what is the camera? Like a fixed dome type camera we have. And here the varifocal cameras in case of our festival halls, right? We have one each. And then this would be like a core switch over here. Okay, the core switches through which we are connecting it to the CCTVs. And this is not a 8-port. How many ever number of the, cameras are there? That much it is like 4 cameras we have. One, two, three, four. So this could be a four-port pole PoE switch only. Okay, this should be a 4-port, right? There should be a 4-port. And the same thing for your the first floor also. Okay, the same construction. And yeah, here we have a ballroom also. So one, two, three, four, five we have. So maybe the same 8-port switch you can continue with. Okay, maybe three would be like a spare also, not an issue. So just you can come, change this to 8-port itself, not an issue. Okay, so maybe let it be like a 8-port itself. Like we have another camera also that I missed out actually, right? 8-port switch, let it be like 3 spare. And now, yeah, like a very focal type of camera. In HE room, we don't have anything. That's just a mechanical room actually. And here we have the switch. Okay, fine. Similarly, in case of, your second to eighth floor, it's typical, right? Second to eighth floor, all like bedrooms. Whether a bedroom, a CCTV is required inside the bedrooms, I don't think so, right? We don't require it. Like just a 4-port PoE switch is enough. What we can do is like, just we can Okay, this is not been made as a block, I think so. Okay, so just let me, or else not an issue. Like we'll select, okay, from the legends over here. Like let me select it completely together. Okay, and let me copy it. Yeah, and like let me switch off this ortho. Okay, and in case of these particular typical buildings, right, right from second floor to eighth floor, what we can do is like it's not required inside the bedrooms, it's not advisable also. So just you can install it, okay, over the corridor areas, like maybe one, okay, one over here and one over here. Okay, just let me change the directions. Okay, let's sorry, let's rotate this one. Okay, while rotating it, okay, you can switch on the ortho and we'll rotate it. Sorry, I am removing it. Okay, so just select this and you can, right, no problem. Like here we have a CCTV. Let me move this one. Like in two ends we used to install, right? Usually, like to focus on each and every area, right? To focus on each and every area. So what we'll do is like we'll move it. Oh, sorry. Because we have not made a block. Okay, if you have made a block, then it would be fine. No issues. Like what you can do is like just select all these things, right? Just select all these things. Like we have a command, right? Like it's a block. So just you can click this block and okay, fine. Let me select this again. I think already they would have made a block. This was an existing drawing, right? Okay, fine. No issues. So just click block and let it be like a cam. Okay, just I'm naming this one. That's all. Right. So now you can check that whether this block is available. Okay. So now you can select this one, right? And sorry. So once you made a block, now you can easily select all these things, okay, and you can move it actually. I don't know whether everything has been selected or not. That's okay. Yeah, now it's a block, so easily I'm selecting it, right? So the same thing, okay, maybe somewhere over here in this column, I'm placing this one, right? In this corner, I'm placing this one. Similarly, this, okay, this let me delete it because I made a, okay, now I made a block, right? So fine. So just you can move this one, okay, like, but the direction is different, okay? We have to just change this one. Like that's what, like you have to change the, you have to rotate this. That's it. That's all, okay? And this FC should be inside. Like, let me move it. Okay, ortho is on. So we can switch off this ortho and let me place it inside, right? And now you can move it. Now just you can, sorry, select everything together and you can move it like uh, this corner. Okay, let it be. Fine. So, like maybe two CCTVs would be enough. Okay, in this case, like just in the corridor area, that we have to monitor for monitoring purpose, right? Usually in hotels, you can check that one, right? Like in the elevator areas, or I mean, in the common areas, we have these cameras, but not inside the bedrooms, right? Not inside the bedrooms. Just in the common areas, you can place like two CCTVs, maybe a four-port PoE switch is enough. Okay, so that's why in the schematic, as you can see this, like right from second floor, right? The bedroom, it starts with second floor. Okay, so from second floor to eighth floor, right? To up to eighth floor, we have two CCTVs, like two CCTV, two numbers of CCTV cameras, and only in case of or ground floor and first floor, like cause we have that festival halls, dining rooms, etc. So we have around six cameras, as I showed you, right? Like four number of I mean, what is the camera? We call that one like a varifocal. Okay, varifocal camera. The another one is like a kind of a dome camera we have, right? Like the usual like dome fixed dome cameras, and Like we have bullet cameras also in case of first floor, as you're seeing it, right? In case of first floor, we have bullet cameras also, and in basement also, like there are four focal cameras are available, right? Focal type of cameras are available, which is not shown over here. But you can show this also, right? In case of your car parking areas also, because here also it's mandatory, right? Here also this is like mandatory in case of your car parking areas. Maybe what is the type we are using? Like we use this focal type. So just you can select this one, right? Maybe again, since it has not been created as a block, what you have to do is nothing but select all these things. Okay, just exclude this line actually, and now you can create a block. So block, okay, like focal cam. Okay, just I'm naming it, and click OK, so that this becomes a block now, right? This has become a block. Now you can easily copy, okay, and you can paste it wherever you like. So here in the car parking areas also, like usually in the corners, we can install this, right? Like a large car parking area, we have maybe one over here and one over here. Okay, like usually in the four corners you can install it, not an issue. And this you can scale it actually. This looks bigger for this particular drawing, so that's not an issue. So just you can scale this one. Okay, that's not a problem at all. So how to scale is nothing but like just let me select this and just use the scale command. So we'll reduce this one. Okay, to a smaller one we have to show it. That's it. Like maybe this is enough, right? So just move it. Okay, and you can place it over here. And similarly, all these things you can just delete these things, right? Delete this one, and you can delete this, and you can delete this too, and just you can copy and paste this one, right? That's all. Copy selection, and you can paste one in the corner or else at that convenient location. Okay, like at a convenient location. Yes, we got a column over here, so I'm just going to place it like in all the four corners, right? In all the four corners in case of your car parking area, right? This is a car parking area, and just okay, this is fine, and slightly you can move this one, right? You can just attached with the wall. That's it. So here there are four cameras. Okay, that's what in your basement area. So we can connect it to a six-port PoE switch. Why the six-port? Because like a two spare we are maintaining it. Okay, that's the thing actually. Okay, just we want to maintain some spare also. Okay, so for that purpose we are maintaining it. Similarly, the rest of the areas here is like a 12 port, but how many cameras we have? One, two, three, four, five, six, seven, eight, nine. Okay, another three spare. So like in even numbers, we have the ports like 2, 4, 6, 8, 10, 12, etc. Okay, so depending upon that. And here it's like again a four port, but we use two only. Okay, we don't have any three port switch, but might be in future maybe some additional cameras would be installed. Okay, for that purpose, like we normally use this four ports. Okay, so all these ports, okay, from each and every switches or from this PoE switches that would be connected to a core switch. Okay, to a main core switch, and then like the normal Ethernet cables. Okay, I mean the Cat5, Cat6 cables would be used, and that would be connected to your monitors, etc. Right, to the monitors, etc. Okay, so this is how like you can work on with an CCTV layout. I hope this is clear, right? This is a simple thing. So whatever the cameras are available, this is your floor plan. Okay, this is nothing but just a normal floor plan because this is typical. Okay, just it's a copy and paste for your the rest of the floors. Okay, just a copy and paste for your rest of the floors. Okay, but maybe in roof also, if you want to provide, you can provide. Okay, that's not an issue. No need. Uh, like we have provided the cameras for each and every area. So while deciding upon the port switches, as I told you, like I mean, including the spare, okay, it comes in even numbers like 2, 4, 6, 8, 10, 12, 14, 16, etc. So with that you have to do, and we have a main core switch. Okay, there's like a router, a kind of a switch or a router. From that we are connecting it to the respective cameras. Okay, I mean the channels like NVR. So how much cameras we have totally like 2 into 7, like 14 cameras, and 14 plus 6, 20, 20 plus 29, around 33, 34 cameras we have. So that's why it's like we use 32 channel, like three terminals are available, like 32 channel, 32 channel, 32 channel, etc. Okay. So All these things you can procure. Like we use three NVRs in this case, okay, with each 32. Maybe one NVR is fine, like, but still 32, 33, and along with the spare ports also. So it's better to go with n number of NVRs, like two to three number of NVRs. This you can design. Maybe in the future you can connect it, not an issue. So for different NVRs, we are connecting the different systems, okay, the different systems. That's it, it is, right? Like as you can see this one, okay. So that's how the general layout it is. And everything we are using a Cat 5 or a Cat 6 cable only, right? We are using a Cat 5, Cat 6 cable, right? So this is all like simple, this ELV drawings, okay, that you can work on it, not an issue. Like maximum your CCTV layout would be available and your data layout would be available, right? Data layout. And I mean, we have another thing, maybe another separate drawing I'll show you for a different building. The data or the voice, okay? The data or voice in the sense as you're seeing it over here, right? So this is that point. Actually, we have some telecommunications rack over here, and these are the data voice points. Okay, from this, these are the outlets. So from here, we are going to connect what we're going to connect the Cat 5 or Cat 6 cables, and that would be terminated in the patch panels or in these racks actually. Okay, in these racks, these are the outlets, right? These are the outlets. Maybe just if you look into this power layout, okay, in this power layout, usually here, okay, data points may not be required. Maybe a Wi-Fi or a wireless point, okay, in the ceiling we can provide. And yeah, like a wireless point is available. Yeah, here you can see this, like the outlets are available, right? These are the outlets we say, right? These are nothing but like your outlets for data, okay, like a data point, as you can see this, right? So this is going to be a data point, and we have two numbers data point, be voice and data, and this is for telephone, okay, for voice, and this is for data and telephone. That means data or voice, a combination unit, right? A combination unit normally would be having this one, and this is nothing but a Wi-Fi and a data point, right? Wi-Fi and a data point. This is a television point, right? This is going to be a television point, and that's what we are seeing it over here. Like normally, like power sockets would be available, and apart from that power sockets, what we need power sockets also, like how it is, like as you can see this with a normal power, and as I showed you in the circuits, right? The circuiting we discussed, and as well as we have the UPS also, like at least one number would be fed with the help of UPS DB for emergency purpose. It's nothing but for emergency purpose, okay, for that point only. And here too, right? Okay, and here we have the telephone outlet, a data outlet, and a wireless outlet, okay, like in case of a dining area. And we have a television point over here, okay, for TV, right? For TV, for TV cables, like the cable TV connections, etc. Then a TV point over here in case of our office. And in office, yes, we need the data and voice points also, right? Right, we need the data and voice also, which has not been shown over here. So okay, it's not a problem. Like you can just copy and install this one, okay, like maybe this one is required or wireless, okay, all these points are required, okay, you can install this in your office also, right? Okay, maybe like you can copy all these things and switch off the ortho, and in office area also we can provide this one. Here there is a TV, so leaving that distance, maybe somewhere over here, okay, or else at this area also you can install. Just a sample I'm showing you, like all like wall mounted, you can see this, okay. So here in office also we can have this data outlets and Wi-Fi points and telephone an outlet. And in case of conference room, yes, of course, we need this one. It's not shown over here actually. So the same thing, like we need the sockets and as well as the, I mean, the outlet also. So here what we can use in conference room, if there is a table, okay, just imagine if there is a table. So we can use a floor box actually, right? We can use a floor box, and inside the floor box, we can install all these points. There's nothing but like, maybe I'll show you what it is. Like these are the points, right? Like these are the points. Maybe just copy it. And sorry, I think I made a scale or something like that, right? So just copy all these points, right? Copy selection and like just place it over here. Okay, just place it over here. I'll tell you what is a floor box is. Maybe wireless. Okay, maybe wireless point is not okay. Let it be. So just we can draw a rectangle. Okay, sorry. So along with this, we can show the sockets also, right? The sockets are also mandatory in this case. Maybe one raw power socket and one, we can install the other one also. The UPS socket also, okay? Like we can provide one raw power socket and then one UPS socket also, okay, for safer side. For safety purpose, if there is no power supply in case of emergency, we can use this one, right? We can use this one, right? So we can show this sockets too. So in this case, it's nothing but like just let me rotate this one. Like I can switch on the ortho and let me rotate it. That's it, right? And this one also, okay. Let's rotate this. That's all. So now just you can copy and paste this one, or sorry, you can move this one in this case. So switch off the ortho actually, switch off the ortho and just you can reduce the size actually before moving it because just let me scale this one. Just for the adjustment purpose, I'm scaling it, okay? But whatever you're scaling it, the same symbol to be used. This is just for, I mean, basic ad, just for general purpose, I'm showing you, but maintain the same thing. Maintain the same size actually, whatever you're creating in the drawing, okay? That should be available. That should be there. And okay, like PowerPoint and as well as, this also you can scale a bit. Okay, let it be. Or I'll make it up to this size actually. Slightly, little bit, I'll scale this one. Okay, so let me move this one. Sorry. A bit problem with my mouse. Okay, so I can just install it away. And maybe all these things also I can scale it if you want, right? Maybe a bit will scale this one. I mean, a little bit, okay. And this should be like reversed actually, okay. So just let's rotate this one. This is fine, but this I have to rotate, right? Okay, like I got a rotate option and yeah, sorry. Select it and you can rotate it. So we can now move this one. Yeah, let me switch off this ortho. Okay. So like this we can prepare. Okay. This is nothing but just this is just a floor box actually. Okay. This is nothing but just a floor box. So inside the floor box we'd be having all these points like the sockets would be available and as well as the data points would be available. Maybe slightly I can increase this size. Okay. That's not an issue. Can just move it. Right. Sorry. Okay. So this is how floor box it would be. Okay. Inside the floor box, we have both socket as well as what we have this. The Wi-Fi data. The data and voice outlets also. Okay. We have the data and voice outlets also. But this would be like inside. Wherever the table is, right? Like at the center of the table, we can. Consider this one. Okay. We can at the center of the table, we can consider this. So like can just move a bit actually. So let me move it and like maybe if this is the table, okay, I'm placing it at the center. So this depends upon the table, like how you're laying it, right? How you're laying it, this depends upon the table. So from the DB, I'm going to connect it from main DB, raw power DB to this socket, from UPS DB to this socket. And how about the connections for these things? Like just Cat5, Cat6 cables that I'm going to connect it to a patch panel, and from patch panel or to a server. That's it, right? I'm going to connect it to a server actually. So this is what like some of the ELV systems. Okay, just I showed you for the reference purpose. Okay, all ELV which deals with either 12 volt DC or 24-volt DC system, and maximum is like only the data cables. Okay, so we have to take care of that data cables, right? And finally, going to be our SLDs. Okay, SLD is nothing but a single line diagram. Already we discussed right in the transformer, right? Should be from the transformer. So this is like just you can see this is an incoming from a build-up panel, and the vertical is nothing but which is going to be a cable, okay, like a 3.5 core 120 square mm. It's an aluminum cable. Similarly, if it is copper, we have to design a copper cable. And this is going to be the main breaker, right? This is a main breaker or an MCCB, we say, okay. Like what is the amperes? 160. So up to 630 amperes, hope you know it, right? It's going to be a molded case circuit breaker. And then with this again, the same cable, we are connecting it with the help of CT. So why this CT is? CT is nothing but a current transformer, right? So why this current transformer is required? In order to connect to meters like ammeters, ammeters, and as well as for relays in order to sense the fault, right? So for that we need a CT actually. With the help of a CT, there's nothing but a current transformer. Like the breaker rating, like this primary would be same, like 160 amperes. The secondary would be either 1 amperes or 5 amperes. In most of the cases, this would be 5 amperes only. Okay, this would be 5 amperes, and we have a control MCB that leave it. And then again, well, coming back to the main panel, okay, this is the main panel. What it means, like this box, you can see this, right? This blue color box. What it means, like everything inside the same panel. Okay, this we discussed in our panel section also. Everything is inside the same panel. Like I have a main circuit breaker, and these are the sub circuit breakers in a single panel. Okay, and these things are different. This is different panel, like different breaker and panel. So that's why this is shown in a single box, right? The CT in the sense, like for all the phases, if it is a three phase for RYB, just excluding the neutral. For neutral, we don't install a CT. For all the three phases, okay, because for all the three phases like RYB, we have to install three different CTs. For simplicity purpose, it's shown just one single current transformer over here, but we have to install how many numbers? Like three current transformers would be required. Hope you're getting it. Okay. Then we are connecting it with the sub-circuit breakers to, to the DBs. Okay. To the DBs actually. So this SLD you can create it, not that tough actually. Just if you know the symbols, just you have to join it and you're going to, you're going to connect it actually, right? You're going to join it and you're going to connect it actually. So here there is again one more SLD. So from an inverter, okay, like from an inverter UPS, like for a basement floor. So what is the breaker size? It's like 25 amperes DPMCB, okay, with this breaker. And everything is inside a single dB, right? Everything is inside a single dB it is, right? Single dB. We have different breakers like 10 amperes, 10 amperes, 10 amperes, 10 amperes, all SP single pole MCBs over here. We are connecting it to different number of circuits. Like this is a 2.5 square mm for power, okay, or maybe 1.5 square mm would be for your lighting. And similarly over here. So an aluminum armored cable with the help of MCB, okay, an SPN MCB or a TP triple pole. I'm connecting it to an inverter. Okay, this inverter is getting the power supply from this breaker, and from inverter, once again, I'm sending it to an inverter DB. Okay, this has been forwarded to an inverter DB, right? And this is what like your DB it is, like your inverter DB, right? Because this supplies from a 5 kVA inverter. The same thing, the same drawing that's shown over here. Okay, this consists of a single drawing, the SLD. So the main cable, the supplies from a main panel. From main panel, with the help of a circuit breaker, I'm supplying it to an inverter, right? Inverter. And this inverter is going to feed all the different loads. That means towards an inverter DB. Which is that inverter DB? This is that inverter DB. Okay. So inside that inverter DB, the same, it's a 25 or 32 amperes you can include. So with that, MCB and an RCCB has also been included, like a residual current circuit breaker also, right? So we have a residual current circuit breaker also with that RCB. We are connected to different loads, okay, like so many numbers. This is going to feed like lighting circuits, power circuits, etc. And along with the spare also, right? Along with minimum spares are also required, right? We require the spare also. And similarly, okay, we have different other DBs like supply from main LT panel. It's 4 core 16 square mm. I hope you know how to size these cables and all, right? And with the help of a circuit breaker, and again, like with the 40 amperes RCCB. So we are including these RCCBs also, like all critical loads. And then like we are connecting it to different circuits, right? Different circuits, you can see this like R circuit, Y circuit, and we have B circuit over here, right? Or Y and B. We have splitted it. That's it. This is a main panel. From that panel, we are supplying it to a particular DB. This entire thing, this blue color line, blue color box, right? This is like a eight-way. Okay, an eight-way DB it is, right? And we have connected it. Eight-way in the sense one, two, three, four, five, six, seven, eight. But all the three phases together. Hope you remember the DB schedule, right? All the three phases together. Like R we have eight, Y we have eight circuits, and B have eight again eight number of circuits, but all are single phase circuits, right? All are single phase circuits. So R1, Y1, B1, R2, Y2, B2. So R1, Y1, B1 will be one way, R2, Y2, B2 will be two way. So completely all together it's going to be an eight way. So this DB should be in even numbers only. Okay, it cannot be in odd numbers, right? Okay, this cannot be an odd number like three way, five way. That's not available. As per standards, it should be eight way only, right? It should be eight way only. Okay, and similarly here also, like this is a 12-way TPN DB. Okay, just you can start practicing, and once you are done with your lighting layout, okay, just prepare the lighting DB schedule, and once you are done with small power layout, just prepare your small, uh, DB schedule for the small power. Then if in case any HVAC or in case any emergency from generator supply or from UPS supply, similar sort of it, okay, like similar kind of it, just you can check it out. Like this is a 12-way TPN for a basement DB, right? TPN in the sense triple pole network, right? TPN means nothing but a triple pole network. Yes, just you have to understand this. And here again, like for HVAC units, like this is your main panel. From the incoming build-up panel, the main LT panel that's feeding, all the rest of the panels. Like we have a PDB1, PDB2. That means power DB1, power DB2. And again, nothing but the power DBs you can see it over here. Okay, like this is LDB, and where do we have the power DBs? You can just check it out. Like it might be over here. Yeah, this is PDB2. This is PDB1. Okay, PDB1, PDB2, PDB3. All these are DBs. Okay, all these are DBs. And how we are supplying it, like as you can see this with main panel for PDB1, PDB2, PDB3. Then we have LDB1, LDB2. So that would be over here, right? So we have an LDB1 and we have LDB2. Yep. And after that, what else we have? Like we have the UPS and inverter. Just now I showed you the inverter also, right? So we have the UPS and inverter circuits like somewhere over here, right? So this is the UPS DB, right? We have a UPS DB. So we are feeding it from taking the power supply, tapping the power supply from the main LT panel itself. And then this is supply from UPS DB. Okay. All these are like from your UPS and from the UPS. Okay, actually from the UPS with the help of these circuit breakers, we are going to feed it to this DBs, UPS DB1, UPS DB2, etc. So that's how it is. So here the main circuit is going to feed to an UPS, and again from the UPS, like so many spares are available. Okay, this is like depends as per your client. Maybe so many spares might not be required. Maybe two, three spares. Okay, that would be fine. Just two, three spares that would be fine. But in this case, like again, that UPS, it's shown like only one normal UPS, right? But again, this UPS circuit has been divided into further, like as you can see this from UPS DB. Okay, so this, we have UPS DB1, we have UPS DB2 again, and then we have a UPS DB3 also. Okay, we got UPS DB3 also. So that's how the connection it is, right? Like DB1, DB2, DB3, okay, from the main LT panel. That means right from that main UPS, okay, UPS. And similarly, I think I shown you that inverter also. No? Just now we checked that inverter, right, over here. So this is your inverter. And again, from this inverter, we are feeding it to different circuits, okay, like an inverter DB basement floor, okay, one inverter DB we have at the basement floor. So for that we are supplying this, okay, for that supplying this. So how we are calculating all this breaker size and this, I mean the cable sizes, etc. That's nothing but like depending upon the total load. Okay, this LDB, it might be 10 kilowatt, 20 kilowatt, whatever it is. So depending upon the load, yes, we have sized the cable, right? Like two conditions, hope you remember. One is with respect to derating factors. First of all, we have to find the load current, and then we have to choose a cable. And after that, we have to check with respect to derating current, like how we are installing the cable, either in the air or in ground or in duct. And after that, yeah, with the current rating, you can size the circuit breaker. And with respect to voltage drop, also you have to check the cable. Okay. So it's nothing but all these breakers, these sub-circuit breakers, okay, we are sizing it with respect to this total load, right? This total load. And this main breaker, like 160 amperes, this is nothing but like depending upon the total load, that's your PDB1 plus PDB2 plus PDB3 plus LDB1, 2, and UPS and inverter. Okay, all these loads together, that would be a total connected load. And 80 percentage of it or 70 percentage, as we discussed in the standards, right? In the previous sessions, I hope you might be remembering that one, right? As per the standards. So just calculate the, I mean, maximum demand, okay, for commercial building or residential building, whatever it is, residential, go up to 75 percentage, not a problem, right? Up to 75 percentage. And for that, we have to size the breaker. And again, for the total load, we have to size this cable, this 120 square mm. I mean, what I mean to say is like, maybe this PDB3, for example, this may be like 10, 15 kilowatts. Okay. For that, my cable size is like 16 and my breaker size is like 63. But this breaker, this depends upon the entire load, the total load. Like for example, 10 plus 10 plus 10 plus 10, like around 50, 60 kilowatts. So for that, I have to size this breaker, and as well as this cable also for that particular load, I have to size this cable, right? It's not like you have to directly count all this breaker rating. It's not like that, right? It's like for the total load, we have to calculate, right? It's for the total load, we have to calculate. So finally, in order to say, is nothing but like, let me draw a simple SLD and I'll show you, right? SLD is nothing but like in AutoCAD itself, we can draw that one. So everything, it starts with the transformer, right? Like transformer, I mean, sorry. So just a circle, okay? So I'm just copying it, copy and sorry. Okay, so this is going to be I'm sorry. Okay, so this is a transformer, right? And this is a transformer, and just draw a line, okay, from this transformer. Like you can switch on the ortho now, not an issue because we are drawing straight lines more or less, right? Side vertical lines. So maybe after that we'll trim this one, okay? So from this transformer, okay, we need a breaker. So where to select this breaker? Yeah, already the breaker symbols are available, right? So where is the breaker symbol? This is like a breaker symbol. A simple breaker symbol is over here, available over here. Okay, so just you can copy it and switch off the ortho now because I'm moving into different directions. Okay, like here, but it's very small actually, right? It's very small. So what you can do is like, okay, just let me scale this one, right? Can scale it. Maybe this is fine. So just move it. Okay. So just you can move this one. Okay. And after this, okay, once again, connect. Now you can switch on the ortho actually. And right. And after this breaker, yes, I got a bus bar. Okay, drawing like this. So this is what this is a bus bar. Okay. So this is like which is like a main MDB, right? Main MDB, and maybe once again, let me select this particular thing. Okay, this particular thing. Maybe along with this line, I'll select like I'll copy selection and let me switch off the ortho. Okay, switch off the ortho and let me connect it to different loads. Okay, like SMDB1, SMDB2, right? Let it be like SMDB1 and SMDB2. And once again, let me include some bus bar over here. Okay, like switch on the ortho now, right? You can switch on the ortho, and here there is a bus bar, and as well as here, okay, there is going to be a bus bar, and then maybe like two number of loads I can connect. Okay, just an example I'm telling you. Like the same thing, you can copy this, right? You can copy this breaker. Like all the symbols are available. Maybe other countries like different symbols also may be available, but more or less it's going to be same. Not an issue. More or less it's same. So just copy this selection and like you can switch off this ortho and maybe one over here, and another load over here. Okay, so just maybe I can connect it to different, whatever the load it is, right? Like maybe a PDB. Okay, for example, let me select this one. Okay, let me copy this and just I'll. Okay, it's not an issue. Just you can scale this one. Okay, just scale it. Okay, this may be enough. So this I'll connect it over here. Okay, so just move it. Right. And similarly, okay, the same. Okay, let me copy this and let me paste it. Okay, so let this be like PDB1 and LDB1. Okay, just an example I'm telling you. Let it be like a lighting DB and power DB, and let me have some two motors and other things also, right? So just let me draw a motor. Okay, like okay, like let it be like what we can call like maybe. Okay, so let it be a pump. Okay, just an example. Let it be a pump. Okay, like a water pump or whatever it may be. Like just P I can mention. Okay, nothing but just a P. It's a pump and sorry. Okay, like pump one. And what I'll do is like I'll just copy this and I'll paste it over here. Similarly here, maybe let it be pump two. Okay, just a sample I'm showing you. So just copy this and you can paste it over here, right? You can paste it over here and let this be like pump 2. Okay, so pump 2, right? Fine. So let this be like pump 2, pump 1, whatever it is. So finally, one simple calculation I'll show you. So if this is the thing for PDB, okay, for example, if it is like 50 kilowatts. Okay, just a sample I'm telling you. If it is like maybe 50 kilowatts, for that 50 kilowatts, I have to size this breaker. Okay, I have to size this breaker, and then I have to size this cable. Okay, I have to size this cable, right? And similarly, if this is like something around 40 or 30 kilowatts, okay, for that 30 kilowatts, I have to size the breaker and I have to size the cable, right? Maybe just a cable sizing document I'll open. Okay, like cable sizing. Just in order to confirm the load, I'll tell you. Like here, you can see this. Okay, if in case if it is of 50 kilowatts, just let me check the circuit breaker rating. Okay, just imagine it's 50 kilowatts. So what is the load it is? Like maximum is 81.8. Demand is like 65.47. Okay, let me consider like the demand load. So if 65 means the next size breaker is like 100 amperes, right? So I have to choose 100 amperes for 50 kilowatts, right? For 100 amperes. So if it is 50 kilowatts, the breaker size should be almost like 100 amperes. So let me copy this one. So just, okay, no issues. What I'll do is like, let me copy the same, okay, this one and I'll paste it over here. Okay. So what is going to be your breaker size is, sorry, what is the breaker size? It's 100 amperes, okay, for 50 kilowatts. So this load is like, I assume like 50 kilowatts, okay. So the breaker rating would be 100 amperes, okay, 100 amperes. And nothing but this is going to be like 50 kilowatts. So what I'll do is like just I'll copy this. Okay, so just under this, maybe note it down as like it's nothing but around 50 kilowatts. Okay. 50 kW. Okay, we call it as 50 kilowatts, this load. And similarly, here maybe like it may be, for example, okay, like just let me copy it and let me, okay, change it to like 35 kilowatts, right? Let it be like 35 kilowatts. So for 35, we'll check in that Excel sheet, okay, in that Excel sheet, like if I just change it to 35 kilowatts. What is my maximum load? Just I'm not checking with the connected total connected load. I'm going to check with maximum demand. 45.83 it is. 45 in the sense the next available breaker size is almost like 63 amperes, right? So here, like it's going to be 63 amperes. So just copy this and paste it over here, right? So it's going to be, I mean, 63 amperes. Okay, 63. So similarly, let this pump 1 be, okay, like just a assumption. Let this pump 1 be. Okay, let me change the rating now. Like let this be like something around okay, let it be like 65 kilowatts, and let this be like maybe a maximum like 80, like around 90 kilowatts. Okay, around 90 kilowatts. So what I'll do, just I'll check for 65 kilowatts and 90 kilowatts, okay, in this cable sizing. So if it is 65, okay, as per our Excel sheet, like 85.11 I'm getting, right? 85.11. That means, yeah, 100 amperes breaker, right? 100 amperes breaker is enough. The same 100 amperes, I can copy this and I can paste it over here, right? And in case of 90 kilowatts, okay, 90 kilowatts, what we have to do? So just change it to 90 over here. For 90, it is almost like 112. So if it is 112, 117 it is. So the next available breaker size is like 125 amperes, okay? So just let me copy this. Let's paste it over here. So it's going to be 125 amperes, okay? So it's 100. 25 amperes. Okay, so we have sized all the sub-circuit breakers, right? All the sub-circuit breakers. So in order to size the main breaker, okay, this main breaker, this is an SMDB, right? So that main breaker rating is nothing but this 50 plus 35. How much it is? Like 85 kilowatts. Okay, 50 plus 35 is 85 kilowatts. For that 85 kilowatts, I have to size this breaker, right? So in that case, like just go back to this Excel sheet. So for 85 it is, right? For 85 kilowatts, it's going to be 111. So that means almost 125 amperes breaker. Okay, we need a 125 amperes breaker over here. So just copy this one and you can paste it over here. Okay, it's going to be 125 amperes. And now here it is, I'm sorry, 65 kilowatt plus 90 kilowatt. How much it's going to be? Like 90 plus 60? 155 kilowatts. Okay, so just substitute this 155 kilowatts over here, right? And how much you'll be getting? Like 202. That means it's crossing 200 amperes. So maybe it's better if you install a 250 amperes, the next size circuit size breaker. Okay, so it's going to be uh, copy selection, and in this case, this breaker size is going to be 250 amperes. Okay. So it's going to be 250 amperes. That's it. And then while coming back to the main breaker, okay, this main breaker rating, depending upon these two loads. So total load, that's it. Here, how much it was? Like 50 plus 35, 85 plus how much this was? Like 65 plus 90, 155, right? Yeah, 155 plus 85. So what is going to be your total load for 155 plus 85? It's like 240 kilowatts. Okay. So for the total 240 kilowatts, we have to size this breaker, right? So for total 240 kilowatts. So just check how much it's going to be. Like it's going to be 240 now. So for 240, what is the maximum demand? Like as per the calculation, it's 314. So 314 means the next size circuit breaker we have 350 amperes, okay, or else 400 amperes. Maybe for a safer side, you can go with 400 amperes or with, okay, fine, no issues. You can install a 350 amperes breaker also. Okay, a 350 or 400 amperes you can use. You can set it to 350 also. Okay, maybe 400 amperes. Okay, that's enough. What is 400 amperes? It's going to be an MCCB, and 125 is an MCCB, 250 is also an MCCB, and almost everything is an MCCB. Okay, because right from 63 amperes we can use MCCB, and if it is up to 63, we can use an MCB also, but it's better to use an MCCB because we have the short circuit protection also, right? Because we have the short circuit protection also. And cable sizing, as we discussed, we have to do it, right? Like maybe just a sample I'll show you. Like it's nothing but like let me copy this. So Okay, fine. Let me scale it. Okay. Let me scale this one. Okay. So the cable size, just generally, I'll tell you. Okay. Generally, in the sense you have to do it like in that Excel sheet as we did, right? You have to do it as we did. But normally for 100 amperes, this would be like 35 square mm. Okay. This would be 35 square mm for 100 amperes. Okay. And for copper cable, okay, it's not aluminum. I'm changing it to copper XLP. Okay, just a sample I'm showing you. That's it. And similarly, okay, the CU maybe just I'll okay. And similarly, if it is 63 amperes, then the next lower size cable. Okay, like let me install all these things and then I'll show you just a sample. Okay, and over here and over here, and again there is a main cable too, right? There's a main cable. Okay, that should come over here actually. Okay, leave that one. So I mean for 63 amperes it should be like at least 25, but it depends upon the length. Okay, this is just the basic as per the standards I'm putting it, but it depends upon the length, derating factors, how you are installing it, everything. So just in order to show it SLD, I'm showing it like this. And again for 135 is fine. And for 125, the next size you can install. Okay, the next size is what, like the circuit breaker is of slightly larger size, right? So you can use 50 square mm, right? You can use 50 square mm cable. Fine. 50 square mm will do. Fine. So that's what it is. And while coming over here, it's again 125. Okay, 125 you can use a 50 square mm, no issues. But maybe 70 also. That depends upon your voltage drop. Okay, this is just a basic standard. I'm installing it. Okay, like 150 square mm. And again, in this case, like for 250 amperes, it would be how much? At least 120 square. I mean, 1795. 95 square mm, it can go up to maybe the next size you can select. Okay, it's nothing but after 95 it's going to be 120 square mm cable. Okay, you can select 120 square mm cable. And what about the final load? The total is 400 amperes. For 400 amperes, like 185 square mm will do, or a 240 square mm. Okay, so it's nothing but okay, maybe this one I can just drag it over here. And the main cable, okay, this particular cable, right? Let's copy this and paste it over here. Okay, all right. Sorry. So this I'll just rotate it. Rotation switch on the ortho. Right. Sorry. Again, select this. Switch on the ortho. You can rotate this one. Okay, let it be. Just a sample. I'll show you. Like switch out the ortho. Okay, so this cable, I mean, and speaking about this particular cable, okay, so there's nothing but sorry, switch on the ortho. Okay, and you can remove it. And okay, so this cable, like 400 amperes, it could be up to 185 square mm. Okay, that would be enough. 185 or 240, okay, as per the calculation. 185 or 240, 4 core. Okay, it's a cop. So this is how you can design it. And what would be the size of the transformer? It's like the total load is of how much, around 240 kilowatts something, right? I think that's what I got it, right? 240 kilowatts something. Yep, it's going to be 240, and we connected for the, I mean, we are calculated for the demand load only, right? Like 240 it is. So maybe a small calculation I'll show you. Like finally we can size up to the transformer also. Okay, just a sample I'll show you. That's nothing but okay, like just a simple calculation. Okay, the final thing will ending our electrical sessions. Okay, that's why I'm showing you all these things. So finally, like okay, your total connected load, how much? It is 240 kilowatts. Okay, for this extra additional, how much percentage we have to consider? Like 20 percentage we can consider. Okay, so 240 into 1.2. So 240 multiplied by 1.2, how much we are getting? Like 288 kilowatts, right? 288 kilowatts. Okay, for this we have to append, apply a demand factor again, like 80 percentage. That means zero point 0.8, right? So just multiply this 288 with zero point 0.8. So if you multiply this to 88 with 0 0.8, it's going to be 230.4, right? 230.4 kilowatts. And now in order to get it in kVA, what we have to do, divide this kilowatts, okay? Whatever the kilowatts we are getting it, divide that by power factor. So what is kilowatt? It's 230.4 divided by power factor, consider zero point 0.8, okay? So 230.4 divided by 0 0.8, so it's going to be again like same 288 kilowatts. And finally, like consider the efficiency also. Okay, the efficiency like 90 percentage, that means 288 by zero point 0.9. So if it is 288 divided by 0 0.9, it's going to be 320. Okay, 320. So the next available transformer size is like 350 kVA transformer we can use. That's it, right? 350 kVA or a 400 kVA transformer maximum. So finally, for this SLD, for this particular load, okay, for this particular load, like this transformer rating is going to be like 350 kVA transformer you can use. So 315 is available, and or 360 kVA or 350 kVA. Okay, whatever is available, you can use that transformer, and including the spare also. Okay, maybe maximum of 400 kVA transformer you can use, no issues. Like, okay, fine. Might be with some additional loads you can use this. I hope you understood this one, right? All the other things you have to do it. Okay, this is what your electrical design is about. Fine, Mr. Tony, Mr. Morosi. Okay. Okay, this is what the design. What I'll do is like I'll be sending you a design document like right from the beginning, like from the lighting. I mean, DB schedule lighting circuit is like around 100 pages. Okay, it's prepared by me itself. If you refer to that and if you read that clearly, then you'll be able to design all the things. It's okay, fine, right, Mr. Tony, Mr. Morosi. Okay, you'll be receiving that document actually. Okay, you'll be receiving that document. Fine. Okay. So now that's it. Like all the best. Okay. Maybe in the future we'll meet. Right. Okay. Thank you very much, Mr. Morosi. And thank you, Mr. Tony. Fine. Okay. Right. Uh, Thank you all. Okay. Maybe I'll just check with the Augmentech itself, Mr. Morosi. Okay. No issues. Right. With them. Okay. Maybe like that. Okay. No issues at all. Right. Thank you so much. Okay. Thank you for your cooperation and patience with me. Right. Okay, thank you very much. Right. Okay, we'll meet in the future. Okay, through Augmentech, if you want any doubts or any clarifications, through them you can contact me. Okay, no problem, no issues. Right, you can just inform them. Okay, you can inform them, Morosi. Fine. Then we'll think about it. Okay. So thank you very much. Right. Thank you. Okay, thank you. Yeah, we have done. Okay, I'll be sending a final document. You'll be receiving that one also. Okay, you'll be receiving that one. So that would be helpful for you. Like step by step process would be there, and you can design the things. Fine. Okay. Thank you. Like let me end the meeting. Okay. Thank you.